Test, test. Good morning, everyone. Thank you for coming in this lovely Dutch summer weather. So our speakers, today we will have 9 speakers in the morning, which is a quite tight schedule. So can I kindly ask the speakers, if it's going to be your turn next time, can you please sit in the front? So our volunteers can help you, and also if you have a speech for like more than 30 minutes, you can get your microphone with our help with a head as well. But if you have a 10-minute speak, then we can just use this microphone. And because we're in the stadium, we have rules of yellow and red today. So if this is going to be only 3 minutes left, I'll show you the yellow card. Then if it's 1 minute left to the question, I'll give you the red card. That means you have like only 1 minute to wrap up your speech. Then we'll have a big question time for the audience. Please do take care of the time keeping, because we have 9 speeches in the morning. We do want to have everyone to have enough time. And I hope Sebastian is here already. Let's give, yes, we have Sebastian. Let's give applause already. Welcome, Sebastian. So let me give an introduction about Sebastian Fitzner, and he is now giving a speech about what's new in the Julia extension of VS Code. And he's starting walking to us right now. Yes, welcome, Sebastian. I tried to find you on LinkedIn, but I failed, quite mysterious. Yes, and I'll help you with this.
Cool. Yeah, hey everyone. As is tradition, this year I will give this exact same talk, exact same title. Once again, what's new in the Julia extension for VS Code? We originally didn't plan to give this talk because neither David nor I had too much time to work on the extension over the last year or so. But luckily, David did find some time to work on it over the last 1 or 2 months. And there'll be a bunch of new features and improvements coming. Some of them are already available in the pre-release version of the extension, so feel free to check that out. It should be pretty easy to just switch over to that if you have the extension installed. But we've decided not to push any of them to the production version, just so the extension doesn't break during JuliaCon, where I assume some of you are using it. So yeah, what's happened over the last year? We've got a few nice new features like inlay hints, notebook debugging, environment variables for debug launch configs, and a lot of changes to the test item framework. I'll just go over all of these in a little bit of detail. Some of you might have seen Cthulhu already. It's a really good package for figuring out what's going on with types in your code. And Zentric has contributed a integration with VS Code. So if you use Cthulhu in the integrated REPL, you can get basically all of the output in the editor as well, which is what you see here. You get type output and can optionally also get warnings about type instability and so forth in the editor. This is also a very extensible mechanism. So if you want to use it for whatever functionality you might build, whatever tooling you might build, you can just use this mime type and show method to instruct the editor to display information in line. There's also some very, very basic static inline hint support, and that's what you can see here. So in this case, we're just printing the parameter names for function calls, which might be useful in some cases, and if they're descriptive enough. So maybe consider not naming all of your arguments X, Y, and Z. Right, what else? David has spent some time rewriting the debug adapter, so that's the backend basically for all debugging in the extension. And it now correctly follows the specified protocol. So it should be easy to use that in various places, like our own notebooks, but also in, wait, I think that comes in a second. Anyways, but also in other editors like NeoVim and so on. We also support environment variables in debug launch configurations now. So if you're using that functionality in VS Code, right, you can write your own JSON file to spin up a debugger in a certain context. Then you can set your own environment variables here. Test items were something we announced last year. There's this whole framework, and now it is also very easy to go into the UI and debug a certain test item, which I think has been a fairly widely requested feature. And something pretty cool that's coming soon with probably Julia 1.11 and newer, but maybe some of this will also get backported. So in that case, it'll be available earlier, is coverage support. So VS Code itself recently got a coverage viewer, just in the mainline VS Code. And in the pre-release version of the extension, if you're on 1.11 or newer, you can already make use of that, and it'll tell you which lines in your code actually got hit by your tests. Right, aforementioned test item integration got improved by quite a bit. Typically, test items are supposed to be completely standalone, right? There's no context from other test items leaking into them. But in many cases, you need to do some setup or inject just a module into each of these test items. So those are supported now with test module and test snippet and this setup argument for test items. And yeah, it'll look like this in your code. Yeah, just like I mentioned some of this earlier already. The debugger now properly supports the DIP protocol. So there's this repository for NeoVim support for the debugger. So if you're interested in that, feel free to check that out. Deepak did great work on that. And I think there's a demo in the Julia VS Code dev channel as well. Yeah, I'm running out of time, so I'll just skip the under the hood stuff. If you're interested in any of that, feel free to check out the packages or just chat with us on Discourse, GitHub, Zulip, or Slack. Or just ask me in person. I'll be around here at JuliaCon, and tomorrow at the hackathon I'll most likely be working on the extension as well. Thanks.
If there is any question about the speech earlier?
Hi, thanks, Sebastian. I was wondering, the new coverage function in VS Code for Julia, does it only work with test items or with any kind of test suite, and is there some setup that we need to do?
So I think it currently only works with test items, but for details you'll have to ask David. I didn't implement any of this, so yeah.
Hey, nice talk. Do you have any coverage for module extension, like static linking, and does it already work?
Sorry, for what?
Module extensions.
Right, we don't. So package extensions are widely or fairly unsupported right now. We have some plans, or I have some plans to get those or to improve support for those, but it's not super easy because the current infrastructure we have for foreign packages basically doesn't really easily allow for this sort of context switching based on the environment.
What do you need to do to activate this Cthulhu type inlay?
Nothing. You just need to run Cthulhu in the integrated Julia REPL, and you'll get a, like in the key bindings section in Cthulhu, you'll get some more items that are related to VS Code. So just lowercase v or uppercase v, I think.
Oh, very nice. Thank you.
Can take one last question.
Is there any plan to change the backend parser from CST parser to Julia syntax, since that seems to be the future now?
Yes, for sure. So part of the test item rewrite that David did is also, or well, part of that was also to write a Julia Workspaces package that does parsing based on Julia syntax. So all of the test item detection is based on Julia syntax. But so far we haven't had the time to switch all of the rest of the implementations over to Julia syntax, but that's definitely in the cards, yes.
Thank you.
Thanks. Let's give another round of applause for Sebastian, the speech. Thank you.
Thank you.
Over here. Yeah, so our next speaker is going to be Luca Bonaldo, and he's going to talk about Gen X, a high-performance tool for electricity system planning here. And also at the same time, Don Jandra is here already. If please, you can sit in front of the row for the preparation. Thank you. Let's give him applause. Thank you, Luca.
All right. Hello, everyone. Thank you for being here. My name is Luca Bonaldo, and I'm really excited to talk to you about GenX, which is a Julia package for studying energy systems and also finding pathways for decarbonization of the power grid and therefore helping fight climate change. So GenX was conceived and developed around 2015 by Professor Jesse Jenkins as part of his doctoral dissertation. And over the years, it has expanded its user base, first by being released as an open source software, and later by registering it as an official Julia package. And today, GenX is used by several institutions and companies worldwide, and it has informed numerous studies on cost-effective decarbonization strategies for power grids of different for different countries, primarily the US and specific states of the US, but also India and other parts of the world. But let's dive into the software. So GenX is an open source software for investment planning in the power sector, which covers production, so generation, distribution, transmission, and sale of electricity to the general public and the industry. And GenX is what is called a capacity expansion model, which is a tool for finding the least cost mix of generation in your portfolio, taking into considerations factors like the prediction of the electricity demand in the future, or changing in the fuel prices, the development of new technologies, or introduction of new policies by government, and so on. So the main objective of GenX is to create an abstract model, or a model of an energy system, and then it runs an optimization model to find the best portfolio of resources to meet the demand on a certain area, given some constraints. And these constraints can be the CO2 emission, so a cap on the CO2 emission, or the requirements on the percentage of clean generation in the final portfolio, or of resources, or other constraints. And also, the analysis can be performed over a single stage or with multiple stages. So you can set targets, you know, at 2030, 2040, and 2050, and then you optimize the variables for the 3 stages. So of course, the GenX is written in Julia. It's about 20,000 lines of code, but the core is implemented in Jump, and the workflow is pretty straightforward. So the user needs to provide a set of inputs in the format of CSV or YAML file, and then GenX loads all the input. It creates the optimization model using Jump. Then the model, which is a large matrix, is passed to the solver, and once the solver converges, GenX writes the output for the user. So from a software design perspective, even though we also export some of the functions, GenX looks more like a app than a lecture library, and after these days I'm super excited about the development of Julia apps. So the user interacts with GenX by compiling this set of data, which can be the time series for the demand for all the regions, or all the attributes of the generators that you want to include. And then you run some configurations, so which policy you want to include in the simulations, or which solver, and what are the attributes of that solver. So, for example, the algorithm that you want to use, or the discrepancy, or where you want to stop the optimizer, and so on. And then you run the simulation and you collect the results. One significant challenge with this capacity expansion model is that they scale quadratically with the number of zones, and also with the number of time steps. And this limits a lot the horizon of the simulation that you can perform, and so HPC infrastructures are almost always needed. Beneath the user interface, GenX is built with modules, where each module defines a specific resource type for each technology. So here I'm presenting some of the modules that we have, and these are the technology for the electricity sector that we have currently implemented in GenX, and the transmission lines are instead implemented as a network, as a graph of nodes and edges. And what is the last thing is that each technology in GenX uses the same template of expressions, or a similar template of expressions and constraints, and this makes it very easy for a developer to add new technologies into GenX, because they just need to follow the same template. And to bridge the gap between this design and the computational hardware, GenX leverages all the Julia features that we all love, so types, classes, template programming, multiple dispatch. We make extensive use of the jump macros for creating the optimization model, and also these features enable a fast development and also high performance, which are two features that are essential in an academic setting. So with this, I just invite you to check out or explore our repository and the work that we do at the Zero Lab. And our documentation gives you all the details for the implementation of all the generators or all the constraints. And also in the documentation, you will find some tutorials to help you getting started with GenX. Thank you.
Any question?
Yeah.
Great presentation. Could you do a short-term simulation with GenX, like for the day-ahead markets in Europe?
So you can not currently, not that I know. So the time step. So you can run 1 year simulation or a multiple year simulation. You can also do time domain reduction and select some like time intervals. But it's the data that we are using. It's more like for a prediction over years, or it's more for a planning in 10 years or 20 years more than a day ahead. But that would be great. Yeah.
So the optimizers you're using that are standard Julia packages?
Yeah. So we use jump. So maybe I can show you here as an example. So we use jump, and then the whatever solver is supported by jump, then we can essentially when you run GenX, you pass the optimizer to the function that runs GenX. So as you can use Gurobi if you have the license, or you can use Hikes, which is an open source one, or all the optimizers that are supported by jump. We are solver agnostic in that sense. Yeah.
Hi, nice presentation. Did you only do generation expansion, not the transmission expansion,
We do
right?
also transmission expansion.
Okay, cool.
Yeah.
And then you have like power flow equations,
Yep.
or yeah.
Yes. We do also the COPF. We are currently improving it, but it's available in our first stage, let's say. But we are, if you go and check, there are a couple of PRs that are now open to increase how we model the transmission expansion, but it's supported right now.
Okay, great. 'Cause, I do think you have some more packages in the same optimization energy system space. If you collaborate with these,
Yeah.
which already have very good power models.
Yeah, in fact, there's a plan to also integrate GenX with the Sienna suite that is developed by NREL, which is in Julia. It's a great package. So that's also a plan for the future.
Great to hear. Thanks.
Yeah, awesome. Thank you.
Oh, thank you. I know there's actually more questions, but we do have a coffee break after, I think, 11:30, where maybe you can find each other and make connections for more questions. And now we have a more interesting, sorry, it's not more, but we have a longer speech for 30 minutes run by Ganjendra. Sorry, I'm sorry about that.
No issues.
Yeah. So the topic is going about how to solve crimes, investigation crimes with Julia package. And I will give you 30 minutes for that. And we'll have a question session a bit longer, which is about 7 minutes in the end. So we'll start now. Thank you.
Good morning, everyone. My name is Gajendra Deshpande, and I am presenting a talk on investigating crimes using Julia. So in today's talk, we'll be dealing with these topics: forensic investigation process, Dobbert standard, and Julia, then some real-world problems. We are not going to discuss only normal crime scenarios. We are also going to consider some digital forensic scenarios also. Now, when we consider forensic science, it's a highly scientific field, but lesser known field. Not many people enter into forensic science. The definition of forensic science is that it's the use of scientific methods or expertise to investigate crimes or examine evidence that might be presented in a court of law. So the main objective of forensic science is to find out the evidence and present it in the court of law. So there is a procedure which investigation officer needs to follow. And if the procedure is not followed, then the evidence may not be accepted in the court. Now, mathematics can be used to determine how crimes are committed, when they are committed, and who committed them. So there will be some scenarios. Let's say, for example, if you find a dead body, then we may have to find out when the death has occurred. That is basically to determine the time since death. Then if you consider the mathematical concepts, so only few concepts are listed here, like measurements, trigonometry, proportions, handling data, probability, distributions. But there can be more complicated and more advanced mathematical concepts that can be used depending on the requirement. Then forensic scientists, they analyze crime scene for possible clues pointing towards suspects and evidence. Then some of the forensic applications which we can consider are lie detection, then determining the time since death, then if it is accident, suicide or a murder when the dead body is found, then calculate the percentage of concentrations, maybe percentage of drugs in the blood, percentage of alcohol in the blood, then compute blood stain thickness, then ricochet analysis and the aspects of ballistics, then DNA analysis, fingerprint analysis, and the list goes on. Now, every forensic investigation process has got these 6 steps. So first one is identification, then collection, validation, examination, preservation, and presentation. In the first step, identification stage, what happens is that investigation officers, they visit the crime location and they entirely seal the crime location. That is because they don't want the tampering of evidence there. And they are going to identify all the objects which they can take it into custody. So there is something called as chain of custody, in which they have to enter the objects they have taken into custody and in what state it was. Now when we come to digital forensics, say for example, if we have to confiscate the laptop or a computer or any computing device, right, we have to confiscate in the present state. For example, if the system is on, we should not turn it off. If the system is on, we should not turn it off, and if it is off, we should not turn it on. That's because there will be some evidence which will be residing in the volatile memory, and if you turn off the system, the information present in the volatile memory will be lost. So what they do is, if there's a desktop, right, so they'll just simply pull the plug and take the system to the lab, so that the information in the volatile memory is preserved, and they can take the snapshot of the entire system for further investigation. And there will be some toy devices. For example, there may be a pen drive which looks like a toy. So such devices may go unnoticed. So they have to very cautiously and carefully identify the objects and take them to their custody. So that's the identification and collection stage. Now, when we are taking the snapshot of a computer for further investigation, right? So what they do is they compute the hash of the original snapshot and the copy of the original data, and they make sure that the hash of both the images or snapshot matches. That is because to maintain the integrity, to prove the integrity in the code, that message or the system or the image has not been modified. The next is the examination stage. So basically in examination stage, they perform examination on the copy of the data, so that the original data can be preserved as it is. And when they are performing the examination, there is a possibility that the software which is performing the examination, that it may alter the data. So the forensic softwares should be such that they should not alter the data. So standard softwares needs to be used. There are some criteria for forensic softwares, which we will discuss it later. Then preservation. After collection, we have to make sure that all the objects are preserved in a proper place at the right temperature with the right security. And there is a plastic bag called as electrostatic bags, which are also called as Faraday's bags, and in those bags these devices or these objects are put, so that the evidence or the objects are not tampered. Then finally the presentation. This is the most important step, because whatever 5 steps we are performing, the goal is to find out the clues, find out the correlation among clues and present it in the court of law. So there is a well-defined procedure which investigation officers needs to perform in the above 5 steps. And if there is some lapse, then it may not be accepted in the court of law. So last step is very, very important. There is something called as Daubert standard. So in United States, the Daubert standard is a rule of evidence regarding the admissibility of expert witness testimony. So there are some illustrative factors which the court has defined and which are part of something called as scientific methodology, as a process of formulating hypothesis and then conducting the experiments. So that is to prove or falsify the hypothesis. Now, there are 5 illustrative factors. So these are general illustrative factors, but these can be mapped to programming languages as well. Now the first illustrative factor is that, has the technique been tested in actual field conditions and not just in laboratory? Then the second question is, has the technique been subject to peer review and publication? Then what is the known or potential rate of error? Then do standards exist for control of techniques operation? And finally, has the technique been generally accepted within the relevant scientific community? So there is one-to-one mapping between illustrative factors and open source programming languages. Now, in 2003, Brian Carrier published a paper that examined the rules of evidence standards, including the Daubert, and he compared and contrasted the open source and closed source forensic tools. And one of the key conclusions of his study was that using the guidelines of Daubert tests, the open source tools may more clearly and comprehensively meet the guideline requirements than would closed source tools. So if there is a closed source tools, how are you going to perform peer review? Peer review will be within the company, but that is not the acceptable factor. But if you consider any open source software, peer review will be by the community. So there may be multiple companies which are involved. So it creates more trust. So now when we map the previous illustrative factors to the programming languages, right, especially the open source programming language, it can be Julia, it can be Python, it can be any other open source programming language. So here, again, we have to ask the same illustrative factors with respect to programming language. Now, the question is, can the programmer algorithm be explained? And this explanation should be explained in words and not only in code. Because we have to explain the algorithm or the functionality or the source code to people who are from non-computing background. So they may not understand the computing jargon. So we have to make sure that they understand the algorithm, they understand the functionality. Then has enough information been provided such that thorough tests can be developed to test the program? So you need to have many test cases here and make sure that there are less and less problems with the software. Then have error rates been calculated and validated independently? Then has the program been studied and peer reviewed? Now if you consider open source softwares or open source languages, right, you will find the entire source code on GitHub repository. Anybody can go to GitHub repository, read the code, review the code, create the issues, right, and contribute. Then has the program been generally accepted by the community? Now you take Julia or Python, right, so they are already recognized in the scientific community. So they are considered scientific computing languages. Now let's consider some real world problems, right? Now when we say math or when we say these problems, many times it's just a simple math which is helping us to solve the problems. So there are already equations well-established equations are there. We just need to use those equations. Sometimes we may have to modify the equations in order to find out the required issue. Now, let's consider these problems one by one. So, let's see how to compute the pressure of a shoe print on a soft ground. Now, here the measurements are taken of the length of the shoe prints and the depth and how far the prints are. Now, if you take the measurements between two footprints, it may give you some estimation about the height of the person. So the taller the person, the longer the feet and stride. Similarly, if the bigger the person, right, then deeper the shoe print because of the weight of the person. Then the formula for determining the pressure in this context will be P is equal to mg by A, where g is approximately 10 milliseconds per square. Right? Then m is the body mass and A is the contact area with the surface. Then similarly, the next case will be to determine suicide, accident or a murder. Now, if you consider the graph here, right? So there are some lines shown, some dotted lines and solid lines. So basically it tells the distance from the building, right? Now, there's something called as launch angle. So if there is accidental fall, the launch angle will be 0 degrees. Because it's just an accidental fall. Nobody is pushing, or when person is jumping, there will be higher launch angle because the person is putting some force. Now with respect to suicide, right? So the launch angle is more. It is between 21 to 38 degrees. Then if it is a murder, then it may be very low. Okay, because the person may be just throwing the body or he'll be just pushing. Of course, the force will be lesser, launch angle will be lesser compared to suicide here. And this is the formula you can use to determine the y. The next is the famous Pythagoras theorem, so everyone knows about it. So now let's see how Pythagoras theorem can be used. Now there's a problem. So the problem is artifact smuggling. So here there's one incident. It's a hypothetical incident here. So here the authorities have video evidence of a possible suspect in the museum break-in. So the suspect was seen carrying a briefcase measuring 20-inch long and 16-inch high by 3-inch wide. So one of the artifacts stolen was 24-inch long and 2-inch wide. So investigators are trying to determine if the artifact was possibly smuggled out of the museum in this suspect's briefcase. Now according to Pythagoras theorem, so when you apply it on the dimensions of the briefcase, so we'll get 20 square plus 16 square is equal to 656, and the square root of 656 would be 25.6 inch. Then the length represents the widest space of the briefcase. So since it is greater than the length of the artifact, so it is conceivable that the artifact was smuggled out of the museum in the briefcase. Then similarly, there is something called as resolution of human eye. So now when we consider an example of witness statement concerning the identification of an individual, so that is valid given that the suspect was some distance away at the time. So we might have watched in several movies, advocate asks a witness, do you recognize this person? So do you recognize this person? Then the person may lie, but there are techniques which we can use and validate whether the witness is lying or whether the witness is telling the truth. So that is based on the resolution of human eye. But of course here we are not considering any additionals like specs or lenses here, because for that again we may have to change the resolution and apply a different formula. Then the fundamental result underlying this is that the unaided idle human eye has angular resolution limit of around 1 minute of arc, which is equivalent to 0.0003 radians. So such a resolution limit means that any two distinct features in an object that subtend an angle greater than this will be resolved by the eye. Otherwise, features will merge and appear blurred and indistinct. So if particular features separated by the dimension d lie at the distance L from the observer, then by the definition of radian, we can require the following condition to hold for the object to be resolvable. So d by L should be greater than 0.0003 radians. Now, consider this problem here. So a witness with perfect eyesight who viewed the suspect from distance 200 meter in daylight claims that he was wearing a striped jumper with the stripes being around 4 centimeter wide. So is this statement scientifically reasonable? So when we put the values in the formula, we get the value of 0.002 radians. So with that we can easily make out. Then next, so if we consider these scenarios, it's all just simple 1 or 2 lines of code which will give you the result, right? You need not have to invest much time in coding also. But that is not true in all the cases. Now, there is something called as hash functions. So hash functions are one-way encryption functions. So without, say for example, so hash functions encrypt the information irrespective of the length of the input, and they generate the fixed length message, right? So the basic goal of hash functions is to prove the integrity of the message, right? So you can compute the hash function using a simple code like this. For example, function simple hash. So pass the input and return the hash. So value to hash will be, I want to compute the hash of the message hello world. Then you can just print the message using simple hash function. And you can see here that it is printing the hash code. Now, what we did in this case is that we added an additional space at the end of the message hello world, and this time it has generated a different hash code. So even a smallest of the smallest modification will result into modification of the hash code. So with this we can easily make out whether the message has been modified or whether the integrity has been compromised. Then extracting metadata. So metadata is data about data. That means, for example, we store information in files, but we need information about files. For example, when the file was created, what is the type of the file, right? If we take a picture, what is the GPS location of the picture? So such information is also very, very useful. So in Julia, you can use the package called as file.io along with other specific packages for different file types to extract the metadata of the files. Now consider this one. So here we are considering few packages. So if you want information about your normal files, say text files, so you can use file.io. If you want to deal with, or if you want to get the metadata of image files, then you have to install a package called as ImageMagick. You want to extract the information of metadata of audio files, for example, the file type, the bit rate, and other aspects of audio file, then we may have to use audio.io. Then you want the information about metadata information about CSV files. Okay, you can use CSV files package. Then extracting metadata. So we install the package, then we are importing the packages. Now we are setting the files for these files, and then extracting the data using get underscore metadata function or schema function. It depends on the package and which function they have. The next is forensic indexing and searching. So here in Julia, you can perform forensic indexing and searching using light graphs and metagraphs package. So why we need to use forensic indexing and searching? So basically, using forensic indexing and searching, we build our own search engine for the evidence which we have collected. For example, if someone confiscates this laptop, there will be terabytes of information on my laptop. So I cannot investigate each and every file. So it is better to create a local search engine on this data. So in this case, such packages will help us to build our own local search engine. Now we can consider using generative AI also. Yeah, so this is how we do it. So we use the packages. Then this is the code. Okay. Then this is the important aspect. So that is called as logging. Okay. So you take any forensic software, logging is an important feature. Okay. Why? Because most of the forensic softwares, they record your activities. Okay. What file you have selected, where you have clicked, what parameters you have selected, and how you have got the output. This is very, very important aspect. Sometimes it is possible for us to get the output using simple Excel also. But in Excel, we cannot record the steps. In court of law, during presentation stage, right, our opposition lawyer, he may simply ask a question, how you have got the output, show the evidence, right? So the one of the important aspect of any scientific package or scientific process is the reproducibility, right? So the opposition lawyer should be able to follow the steps and get the same output. Then he will trust the software. So you have to make use of logging softwares which will record each and every step. How much time I have? Okay. Okay, fine. So I can just take 1 minute and just complete it. Yeah, I'll just wrap up. So similarly, this is a digital forensic scenario where we want to detect the case of money laundering. So this is a money laundering scenario. And you can apply Benford's law and to detect whether there is a possible case of money laundering. Yeah. So conclusion is that forensic investigation is a highly scientific process. So since Julia is scientific computing language and conforms to Dover standard, it is one of the most suitable languages for developing forensic tools. So in forensics, accuracy of clues and evidence matter rather than the performance of the application. Thank you.
Any questions regarding to the speech? Before that, I have a question actually for you, because I know you own a company. The name is ISEC Cybersecurity. I wonder how you are applying what I've mentioned in the real cases with your company.
So generally what happens is that we get some cases from local investigative agencies, right? So we work with them, and depending on their requirement, we develop a small tools and give it to them.
Are you using Julia there already?
Yes, we are using Julia as well as Python.
Thank you. Any more questions?
I was just wondering about like the lie detection, because that's been a very controversial topic, and how is that translated legally? Is that taken as actual proof that the witness is lying? I don't know.
Yeah, so when you consider all these softwares, so there will be many false positives and false negatives, right? So these softwares will just help us to provide us the clues, right? So again, it is the duty of investigation officers to further collect the evidence and correlate with other pieces of evidence and then take a call. Yeah.
Anyone has a question?
I have another question, sorry.
Sure.
So how is Julia, as you mentioned, there is actually a more suitable language in case of their double standard. How's Julia better than other programming languages in that case?
No, actually when we discussed one of the slides where we had discussed Dover standard and Julia, right? So there is a study done by Mr. Brian, right? So he has concluded in his study that open source languages or open source softwares, they are following the illustrative factors laid out by the code more than the closed source softwares. So it's not only about Julia. You take any open source language, right, which has these illustrative factors, it's better. For example, is Julia peer reviewed and published? Right, it's already there on the GitHub, right? And apart from that, there are many scientific papers which have been published, right, which have validated the work of even Julia language and the packages, right? Then there are many tutorials which explain how the code works. So if you see there clearly, right, and there's a strong community also, right? So all these factors, they make Julia suitable for forensic investigation purpose. So there have been very nice packages in our language also. So if you go to a website called Forensic Stats, right, so you'll find wonderful packages in wonderful packages for forensic science. But the only thing is we don't have them in Julia. So the alternatively, we can take the ideas from there and we can start developing the packages.
Thank you for that,
Yeah.
Gandhara.
Thank you.
Yeah. Let's give another applause for the speech. Thank you for the speech today. Colab? Yes. Do you have? Yeah, can you use this one? But do you have a USB? Do you have a? Oh, it's yours. Well, preparing this topic is about a experimental search system for Julia community. And we'll have 3 minutes in the end for questions.
Can you hear me all right? All right, I'm going to speed through this as fast as I can. Sorry about that delay. I'm here to talk about something I've been really excited about for a long time. I've been interested in the search space for a while and have found Julia to be particularly well suited to a lot of problems that come up in search and information retrieval. So I'm talking about T-Search, which is an experimental search system that I've been working on that I'm releasing to the Julia community as a web service. So first I want to ask, what is important information? Ranking is a very, very difficult problem in information retrieval. It is the difficult problem. PageRank is the elephant in the room here. This is an excerpt from the PageRank paper from Larry Page and Sergey Brin et al., where they describe the random surfer model. They essentially say, if you took a random surfer, someone just clicking around on the web, what web pages would they be most likely to land on? And it turns out that if you do some interesting math with this, it generates an extremely good ranking system. That's what launched Google. This is a very, very rough view of it, but effectively you look at every page that links to your page and then follow those through for a long time. It's surprising how good it works. They say that it works particularly well for underspecified queries, and that's what I want you to take note of. What is an underspecified query? I want to talk about overspecified queries, which get underspecified answers. I don't know if this is an experience that people have shared with me, but I find Google often is not able to really understand the semantic information that I'm actually looking for, especially with Julia-related information. It's a small community, it's a small ecosystem, and so it certainly makes sense, but it's been frustrating for me. This is a web search showing results mostly from Stack Overflow, most of which were before 2018. And for certain answers, right, the language changes quickly. I want to make sure I'm having the right information, so I don't know if I have the right information. Searching for linear algebra, Julia. The first link is to Julia 0.6. There's no documentation at all in any of the top search results, even down to the 10th. This one was shocking to me. I was searching for the Julia dates package just quickly. And the first website that came up was a dating site for wealthy men and ambitious girls. So on the one hand, this is minor inconvenience. On the other hand, for a tool as extensive and dynamic as Julia, I think we ought to have a tool that allows us to seek this information a little bit more precisely. This is a Julia user who posted on Reddit, how do I find the documentation for a package? I'm not really sure how to do that. And then the responses were essentially 4 different ways of doing it. You got to read the source code, read the readmes, use the REPL help mode, all of which are very helpful and are very correct. But effectively what my thesis here is that the Julia corpus is hypertext weak. And a hypertext analysis on the Julia corpus is not going to, fundamentally can't understand the real structure that's there. So what is the Julia corpus? The Julia runtime is the center. Around that is everything else. The docs, the issues, PRs, discourse, source code, Slack, etc. And how much of this is on the web? A lot of it. The docs, the issues, those are all web-based. But the Julia runtime is not. And if that is not accessible on the web. You know, there's source code, you can see the URLs, but if I'm asking for the print line function, there's no URI for that function in particular. You can see the source code, but not the runtime. So I've been working on T-Search. I was hoping to have a demo launched for you to use today, but it's probably going to be a couple more days. It's a precision search tool that's structured. It's a structured index that's built around the Julia runtime, using these primitives as the key tokens on which all of the other search and indexing falls down from. You can think of it kind of like a methods with on steroids. I'm going to just blaze through the end here, but it's an index structure that resembles Microsoft's Bitfunnel a little bit, which is what powers Bing. It doesn't use a reverse index like Google. It uses a forward index with very fast capabilities, using techniques taken from static flow analysis. And it very accurately, very faithfully represents Julia's data structures. It's, all right. Anyways, there's a lot of exciting stuff here. Feel free to find these slides online. And if you are interested in getting use of this, go ahead and scan that or go to tsearch.org, where you can register your email, and I will be happy to get people's feedback about all of this. Thank you.
Thank you, Caleb. Yes. And our next speaker is, thank you for that. Our next speaker is going to be Leo Butty, and he's going to talk about inferopt.jl. Let's welcome Leo.
Is there an internet connection?
This is
no.
an internet connection.
Okay.
Yes. Sessions, so at least we'll have enough time about the speech itself. And if you have any questions, we do have cafe sessions or at the lunchtime where you can connect and ask individually. Sorry again about this internet issue.
Okay, so hello everyone. I will present you the Julia package inferopt. So what is it about? So it contains state-of-the-art tools to incorporate combinatorial optimization algorithms into machine learning pipelines. And it is compatible with machine learning and autodiff ecosystem in Julia, such as Flux and chain rules. And it is now part of the new GitHub organization, Julia Decision Focused Learning. So why do we want to use combinatorial algorithm inside machine learning pipelines? So there are two reasons. The first one is that it increases the expressivity of machine learning models by having the possibility to have combinatorial outputs, and it can also leverage algorithms for easy problems to solve harder ones. The main difficulty of including combinatorial algorithm inside the machine learning pipelines is the fact that combinatorial algorithms are piecewise constant, and we do not have informative gradients for machine learning. So inferopt provides layers and loss functions useful for this. So let's start with simple example. Simple application. So here we have a problem of finding a shortest path on a map. So you have an input, which is an image map, and the objective is to compute a shortest path from the top left to the bottom right corner. But the problem is that we don't know the actual costs of each cell. So we want to build a neural network that takes the image as input and predicts some costs, and then we use a shortest path algorithm such as the Dijkstra algorithm to compute a shortest path between the two corners. So our dataset is a set of pairs between images and paths, and we want to imitate these paths. So let's build a pipeline in a few lines. So first of all, we can use the infrared benchmark package to download the datasets. So here we generate a dataset with 50 samples, and so we can plot one of the samples. So we have the image, the true weights we assumed we don't know, and the true path we want to imitate. And first of all, we can build. Okay, sorry. Like this? Is it better? Okay. So first of all, we can generate the neural network. Here we take a convolutional neural network, and we see that at the moment it's untrained, so it does not predict very useful costs. And we can also generate the combinatorial maximizer using the Dijkstra algorithm from the graph.jl library. And so we see at the moment we predict only a straight line path, but we want to output the better path from the dataset. So now that we have the pipeline, we want to build a loss function which is differentiable. So let's try to compute a Jacobian through our maximizer. And as I told you, it does not work. Here with zygotes, it fails because we have mutations in our algorithm. And if we use another package which is forwardif, it works, but it gives 0 everywhere because our algorithm is piecewise constant. So it's not very useful for learning. So what we do is we use inferopt to and we use a perturb wrapper that takes as input our maximizer, and it modifies our maximizer such as it outputs now a continuous matrix, which is very close to the initial path, but it's continuous, and then it allows having informative gradients. As we see here, we can compute now the Jacobian using zygotes, and we can also define a loss function for which we have also gradients. And when we have this, we can build a full pipeline and build the training loop. As usual, here we use flux to train, and we optimize the loss function over our training datasets. And then we can just see how we perform on the test dataset. So here we have the input image. These are the weights we predicted. So we see that he predicted high costs on the water spaces and the rock spaces, and then our maximizer just computes the right optimal path. Thank you.
We will have time for questions indeed this time. Thank you for that time. Any questions? I guess they're not prepared because I told them to ask later. But thank you for the speech. Thank you. Our next speaker is Vibhath, and he's going to talk about optimization.jl. And because there are people coming for you to speak, and if it's okay, we can start at 11:20 sharp. Yes.
Is the
Yeah, we can see it.
Hi everyone. So I'm Vaibhav. I developed the optimization.jl package. I'm a grad student at MIT right now. So basically this talk, I aim to cover some of the motivation of why optimization.jl exists. That has been a question, I guess, I've come up with an answer for after a bit of soul searching over the last year. Yeah, and then I'll just tell you what have been like the recent developments, some of the interface changes and new features that are available. Cool. So like what are we talking about here? I expect a lot of you will already know this. This will be boring, but basically we are talking about optimization problems, which is this generic way of describing a lot, writing out a lot of applied mathematics, which is you want basically a minimizer for a function that you define, which also needs to respect some set of constraints. Cool. How can you do that? Well, you have these things called oracles that you can use that basically tell you more about the problem. They tell you about what the parameter space looks like and what the thing that you're interested in, like the loss function, looks like over your space. It could be like any kind of a manifold or like the Euclidean space. So yeah, basically these the definition of these oracles can change a little bit depending on what kind of a space you are on. So how do people do that on computers? Well, there's like a ton of really great software that exists for optimization, and especially in Julia, like Jump is probably like one of the most successful projects that we have. And there's like other ones that are really great as well. But what I would like to sort of point out here is like there have been typically two approaches to building optimization software. One has been this algebraic approach where you set out by defining your problem explicitly. These tend to be people with a good training in optimization. They know exactly what they are doing. They are able to write out a lot of details about their problem. So that's more like the structured optimization perspective. But then you also have people doing machine learning, and where you basically say, this is my data, this is my loss function, let stochastic gradient go brr, right? But so those softwares also exist very separate from each other. You can't really do machine learning in Jump, for example. Well, you could, but even they don't really encourage that. So the idea here is that can we try to unify these two approaches to building software for optimization? And the other thing that sort of plays a role here is this model-centric API versus Oracle-centric API, which I would also sort of tie in with the two approaches I talked about before. The model APIs tend to be more dominant in the algebraic software, and these Oracle APIs are like the typical machine learning libraries that you use. And I've listed out a bunch of examples of these kinds of APIs that are available. So what does optimization.jl offer? Well, the aim is to sort of extend this overarching goal of SciML, where we are trying to build symbolic numeric tools and be able to use, as depending on your use case, and also to sort of improve each other, right? Like there's a lot of things that you should be doing algebraically, and there's a lot of things that you should be doing numerically always. But mixing them can really help you. So optimization.jl basically has two interfaces. One is like the functional interface, which is the Oracle-based APIs that I was talking about before, and the algebraic interface through modeling toolkit. This is just like a bunch, sort of a pseudocode to explain what that looks like. And yeah, so this basically has been like the enabler for a bunch of development that I'll talk about next. I'll start off with like something you might not care too much about. It's kind of internal, but basically now we have out of place optimization functions supported. What does this do? Well, it helps you be able to write, it helps you avoid a lot of like scalar indexing and stuff like that. So you can actually start thinking about writing out oracles for GPUs, which is not, it's tough. Anyone who has worked with GPUs and AD tools will know that it doesn't always work, right? And yeah. And then we have recently added a native, well, I wouldn't call it native because the actual implementation is in Fortran, but we have this LBFGS optimization solver now available right out of optimization.jl. I have also implemented an augmented Lagrangian over it to be able to handle just generic nonlinear constraint problems. I can quickly show you an example of that. So basically it helps you cut down on the number. So one of the issues that used to be was because of all these solver wrappers, right? You can end up having to like load 6 packages just to run a simple optimization problem. But now I can just load optimization and an AD package, and then I can just use LBFGS to actually get pretty good results. And I actually believe like the LBFGSB implementation that we have wrapped is actually like one of the most robust, because of its line search, like one of the most robust optimizers I've used. So yeah, I hope you guys think that too. This is just the API I showed in the code. Then we have actually added support for ensemble problem. If you are a SciML user, you know ensemble problem is this way of being able to run copies of the same problem using different initializations. For our context, like in optimization, it would be like different initializations. Why can that be useful? Well, when you are in a low dimensional setting, it can actually be pretty effective to just use like a multi-start optimization technique. So I'll just show you a quick example. Again, I'm still using the Rosenbrock function, but now I'm using like BFGS from Optim, and I'm just going to run it for 5 iterations. So you see I get an error of around like 0.25. But if I like now, I'm just like literally randomly sampling on the space and initializing 4 different initial points. And by doing that, I can like actually get, like almost 100 times lower objective for the same number of iterations. So for low dimensional cases, this can be very useful. We have, new wrapper solvers for Prima and manopt. Prima is this Powell's derivative-free methods, and manopt is optimization on manifolds. So related to that, we have recently added a sort of a middle layer in optimization base that can allow you to do some structural analysis on problems. And this structural analysis is basically the disciplined convex programming and this novel. We recently put out a preprint with some, I put out a preprint with some collaborators from Harvard called disciplined geodesic convex programming, which is extending this idea of disciplined convex programming to manifold optimization problems. It's only limited to symmetric positive definite manifold with the canonical affine invariant metric. So it's very limited, but I think it's a useful direction to start thinking about, because it actually helps you make all those guarantees about global optimality for problems that appear to be non-convex in the Euclidean setting. But so I hope you can take a look at the paper and find it useful. I have the code for that just to show you what this looks like. And this is like just a regular optimization problem. It's pretty trivial to see that it's convex is just the sum of exponential and square. But now when I set structural analysis equal to true in the optimization problem and run the solver, it actually prints out a certificate of its convexity. And if you have a successful first order convergence on a convex problem, you know that it's the global optima. And then you can actually do this similarly for a manifold optimization problem. Here I'm doing this problem is called as the Karcher mean problem. It's basically trying to find the geometric mean of symmetric positive definite matrices. It's known to be non-convex in the Euclidean setting, but I can basically use the same infrastructure I was using before, set structural analysis equal to true, and pass the manifold, the symmetric positive manifold that I'm defining the problem on. And now, so you can see that it's, it has a unknown curvature, which it doesn't necessarily mean it's non-convex, but it's basically mean that you can't recognize the structure using disciplined convex programming. But as you can see, it prints out that it's geodesically convex. So that can be useful in some problems, especially in statistical estimators tend to use log determinant, for example. So that can be useful. So that's it. There's a bunch of future work that needs to be done, like always. And so I've just listed out a few bullet points I could think of. Yeah, that's it. Thank you.
We will skip the Q&A session, and we're inviting our next speaker, which is Thomas Bolson, about music tuning with Julia application. Thank you again.
Okay. No worries. Thank you.
Within 10 minutes.
Got 10 minutes now.
Yeah.
Yeah. I forgot to put a sticker on it. So I need to play some sound. Yeah, yeah. Is that gonna work? My colleague is sick, so I'm here, and then I saw you yesterday. So. Yeah. Yes. I'm muted over the speakers, but I'm gonna listen if I receive some.
You don't have a mic for the headway?
Sorry?
So
Like for head.
I can put this on too.
Yes,
Yeah, no problem.
because I need to use my hands.
Okay, then I turn this off. Welcome back. Our session is going to begin in 1 minute again. And I think all the audio settings done. And if you have any food or chat, please finish your conversation within 1 minute. And we will have Thomas here giving us a speech about music tuning, which is quite interesting with Julia. It's quite different from everything we had in this morning so far. So yes, let's get ready and welcome Thomas for the speech.
Thank you. More specifically about music tuning. So tuning is putting frequencies onto notes, and this is a package that I wrote for this. It's not registered yet, so you can still influence the name if you don't like it. I call it tuning systems for now. So we all know if you look at the normal piano, we have the octave divided into 12 equally distributed frequencies, the 12 semitones, and they each have a frequency ratio of about 1.06. So the package has a function to generate these equal tempered scales of any length. So here it is of length 12, the normal one. And it also has a method to generate a data frame out of this so that we can do computations on this. It can also play, and this is going to be the interesting part. So it can actually play a scale, and what I do here is, so I have the note names here, then I just do a split, then the note function generates a note, the tone then takes that note plus a tuning, and in this case it's the equal tempered 12 tones, and then it generates a sound with a synthesizer, and then it plays this out of that. So it seemed to work this time, that was nice. So some sounds sound particularly nice. So for instance, the octave, or the fifth, and they are, here we play them together. And you can see in the way this is done, so here in the first one, I just, if I take the sound on the vector, it plays the chord, and if I broadcast it over the vector, then it plays them in sequence. So that, I think that's a pretty nice interface for this. Right, so how well is the piano actually tuned? So if we look at the difference between the perfect fifth and then the seventh semitone on the piano, we can see on this number up here that they are pretty close. They are within 0.1%. Or something similar. So how does this actually sound? So we can hear if we play them together, we can hear that there's actually a small beat tone like this. If we play them without play them in succession, you need to have very good ears to hear that were actually two different tones. So this is some of the fun things that you can do. There's also plot recipes that will then plot the two together so that we can see how they look as functions. And this was the beat tone, so you can also, if you plot this over the beat frequency, which is 0.75, which is the difference between the frequencies, then you see this. And in order to do this in a good one, you actually explicitly have to sample. And the sample method is doing that at a normal 41K, and also for the plotting. Okay, so the equal tempered tuning is so natural, it spreads evenly, why would you ever have anything else? But it turns out that other cultures, other times have used other tunings. So one of them is, it's this guy, Pythagoras. Apparently, I don't know it, I'm told, he was thinking about these things, and he noticed that if you take this fifth, which sounds perfectly, and if you apply it 12 times, so you know mathematicians, if it works once nicely, then just do it twice, just keep doing it. If you do it 12 times, you actually get to something which is almost 7 octaves higher. And the difference is this little bit, this funny looking fraction, which is called the Pythagorean comma. And this comma is actually not so small. So if I, which slide am I on? Right, so, sorry. Okay, I'll skip that. So I can also play the comma, and it has a beat frequency of about 7 hertz, so it can it's actually hearable. Yes. I want to introduce 2 other concepts that the package understands. So there's pitch classes, which are basically equivalence classes of tones given a module or an octave. And there's cents. So cents are the 1200 division of the octave. So if we do this thing about going off the fifths and do the pitch class and then take the cents, we can see that we get something which is almost a integer times 100, but it's overshooting by about 2 every time. So when we've done it 12 times, we're overshooting by almost 24. So in reality, the Pythagorean tuning is sort of halving this error by going both ways around the circle of fifths and putting it all the way over to the tritone, which is F sharp, no pun intended. That is what is actually called the Pythagorean tuning, and the package has that inbuilt. So I just want to do a little bit of plug for this tuning, which is called just intonation, and where all of the 12 semitones are in nice little fractions, which are composed by numbers that are multiples of 2, 3, and 5, so it's called a 5-element tuning. There's another plot recipe in the package to plot tunings, to compare them on a cent scale. So here we can see how they look if we compare them together. And then the last thing I want to talk about is the harmonic series. So if you take the first 6 harmonics, or the first 5 actually, you get 3 different frequency ratios, and that is actually the major triad. Yeah, I would also like to play that, but my history just went wrong. So I hope I get to it in the end if I have time. Anyway, here's how it looks on this. So if we take a lot of harmonics, we can almost get this tuning, but not quite. I wanted to get to this slide because one nice thing about the just intonation is if you take the sort of 3 major chords, if you play a guitar, you know 3 chords. It's these 3 chords. If you take those, then for all of these 3 chords, you actually have the same ratio between the frequencies, so 4, 5, 6. And if I'm a little bit lucky, I can make this play so that I can and this was actually what I wanted to sort of investigate with this package, was how does this actually sound? I mean, if I take this major triad and play it in these different tunings, then how does this actually sound? And while you're thinking about your questions, then I'll see if I can find this in my REPL history so you can hear it. So here comes the... So this is the just tuning, and if we hear it now in, let's see, here's the equal tempered. You see it's not so nice, it has a little bit of beating, and if we take the Pythagorean, it's actually pretty bad. So let's go back to the just one and then end that. Perfect harmony. Thank you very much.
Oh, this very interesting speech. Any questions about what happened earlier?
Yeah, I forgot. Thank you for all of the great packages of the Julia Music organization. And this was inspired by these very interesting blog posts by John Bass. So check them out if you're interested in things like that.
I just wanted to ask how much you enjoyed the keynote yesterday.
Very much.
And then I just wanted to suggest that you put music or something somewhere in the package name, because if I hear tuning, I think of like machine learning stuff, and then I was like, this is really
music
cool.
tuning systems is probably a better name. So it's good that I didn't register it.
It's very, very cool. Thanks.
Which kind of waveforms you use for the examples?
All of this is just sine waves.
Yeah, because the beating is more evident when you use, because usually these are a bit more washed up when you have.
Sure, but this was
harmonic.
for analytical purposes, so that's why I used the sine phone to make this clear. Of course, if you play it on a real instrument, it doesn't sound that bad. Otherwise, you wouldn't make music today, I guess.
Okay.
Question?
And thank you for the day, Thomas.
Thank you.
All right, our next speaker is going to be Colin Swannen. He's here. And the topic is about parsed messages in Julia. And yeah, you can use this one or this one.
Okay, let me try my ear.
Okay, you can just plug this. Yes.
Oh, this one I need to.
Oh, you need to see. You can also use. We do have adapter. Yeah, you can use yours if that works. Thank you.
All right, so I'm excited to be here. I'm coming from the Data-Driven Social Science Initiative at Princeton University, although this project is somewhat of my own side project, and I'm very happy that DDSS allows me to do these types of things. Last year I came and gave a long, complicated talk, so today I think it's going to be a short, simple talk, and probably what you're going to learn is that there's a data source, and now Julia has a package that can parse that and make a nice database for financial researchers. And I have QRs for the slide deck or the GitHub repo up here if you're interested. All right, so some quick background. NASDAQ provides something called Total View ITCH, and this is a data source for high-frequency traders or anyone who wants to have a sort of real-time view of the NASDAQ market. And so what it is a stream of binary messages. So traders get this in real time, and it basically allows these traders to reconstruct the state of the system. They have nanosecond timestamps on them, and they come in a variety of different types. So you have things that are system messages, order messages, and trade messages, etc. And these all convey different types of information, the most important of which is people basically saying, I'm willing to trade a certain amount of a particular stock at a particular price, and then adjustments to those orders. So this has a specification. This is the Total View ITCH specification, and each message comes in as actually it says how long the message is going to be, and then it's followed by the message. And the message consists of a type, a single character explaining what type of message you have, and then something custom to that particular type of message. So these are examples. You could have a system message that simply says, this is the time in the market. And then you could have an add message, which is indicating that someone's willing to trade a certain amount. And then you'll get a subsequent delete message or execute. And the important thing here is that those subsequent messages don't contain all the information to say what is actually going on. You need to refer back to the original add message. So there's a bit of work there. So traders purchase this, but for academic researchers, NASDAQ will give you the data if you ask nicely, and they'll give you all of the data as much as you want. You simply need to download it. However, this is a little bit daunting for academics and finance. So this is sort of too technical a process for most folks in the field. They really want to focus on their research question and not figuring out how to make use of this data. However, it is a unique data source that really, if you want to get a full view of the market, this is the only way to get that. So the goal here is to build an open source parser for this research community. And the requirements are that it has to be able to parse all the messages, and it has to do something called reconstructing the limit order book, which means that at every point in time, we need to know the number of shares at each price that people are willing to trade for every single stock in the market. And this has to be reasonably fast and easy to use. The status of the package right now, we can extract all different messages and different formats. So there are 2 formats. We extract all the messages. I currently don't store all of the different types of messages, so we'll say that's okay. We support both formats. That's good. Supporting multiple storage backends. So right now we support 2, but we need to support more. And since this tool really just does one thing, it would be great if it had just a single command line, and maybe we can put that in when the app feature discussed earlier in JuliaCon is in place. So sort of quickly, right now the way that you would parse something in Julia is construct a parser, and you specify a backend. So here I'd specify the file system, which is one of the backends available, and where you're going to store it. And then you simply call using that object the file that you want to parse. You have to specify a date because we don't actually know the date. The file formats don't give a date. And you can say which stocks you want to process. Here I'm doing tickers A and B, and you need to tell it the format because it can't know that from the file itself. Data storage, so we have 2 ways of storing data right now. The default is to just store everything in CSVs. This is the format that most financial researchers are comfortable with, but not very efficient. We can also store it in MongoDB. Why MongoDB? You can ask me later. It's a strange choice, but we can do it. And if we store it in CSV, then we store it in a hierarchical format where it's organized by ticker and then by date so that you can look up a particular stock date, which is how a lot of research is done. If you need a different format, Julia's generics and abstract types to the rescue. So there's basically an interface for a storage backend, and some of these are optional methods. A couple of these are required. If you have the required ones, then you should have yourself a working storage backend in, say, Parquet. And so the roadmap for the package right now is improved message type support. So we're actually storing all the things that we're able to parse, and then additional storage formats, making it a command line tool, and then some other things like there's some speed ups we can do, and just improvements to the dev process. All right, so thank you. That's all I have.
Questions for the speech? Yes.
Is this for like real-time software, or is this like research software that will just be doing stuff that happened in the past?
Research. So they provide a single file for each day. So yeah, this is actually the historical TotalView ITCH, but I thought it was already a long name, so I stick with TotalView ITCH.
And then I also want to ask for the speed of the computation of this sort of field of investment prediction, stock market stuff. Do you think that there's space for Julia there, or is it got to be way even faster?
Oh, I've compared this to Rust, and it's the same basically. I mean, better programmers than I could probably optimize this in a way, but I had very, very similar timings between those two. Yeah.
Sick. Anybody else? Questions?
Thank you, self-organized, I see. Thank you again, Colin, for your speech. And our last but not least speaker today. Yes. So, Abel, pronounce your name correctly, I hope. Yes. And yeah, this is going to be the last one. We're going to have 30 minutes on the topic. It's about JSO Suite. And we will have around 7 minutes question session in the end.
Great. Okay, so thanks a lot. Thanks everybody for coming. It's great to be giving a second talk at JuliaCon. So today I'm going to talk about JSO Suite. This is mostly a work by Tanguy Migaud, who could not be here because he's on the other way. He will be at the Jump Dev conference, so if you're going to that, please talk to him. And the slides you can find in the QR code. So JSO Suite is part of the Julia Smooth Optimizers packages. So JSO stands for Julia Smooth Optimizers. I will use that a lot. And I just want to show the main takeaways if you need to leave early or hungry for any reason, or if you just want to see this slide. So JSO Suite is a nonlinear optimization interface, which means it's like I want to optimize things. I just want to get the user-friendly thing, right? It's backed by Julia Smooth Optimizer, so we have developed a few packages over the years. Julia Smooth Optimizer was created in 2015. It is mainly research focused, so we have worked in a lot of packages for cutting edge solvers, and now we are looking a little bit for the user friendliness. And the main idea of JSO Suite is that you have a single package that you load using JSO Suite, and you have the solver selected automatically based on what you have. So you just create your problem in the simplest way. You just give the objective function, and it works. It will use what is loaded. So if you have more packages for optimization, IPOpt being the most famous one, you can use that as well. And we are looking for enthusiasts in this field. So most of the development in JSO is based on research. So user friendliness is not something that we are really proficient. So if you're interested in just helping out to give your opinion, or even just I know how to make things better, or if you're just interested in optimization in general, please get in touch with us. Help us make JSO better. Okay, so Julia Smooth Optimizers, you can find us at jso.dev. It's this organization since 2015. We started all of this when we decided to streamline optimization solver development, which essentially means you're doing PhD in optimization solver development. And when you normally have to do that, you have to worry about where are things coming from. So you have an optimization problem that's coming from somewhere. For instance, pretty common situation. You just have your advisor giving you a file saying, this is our objective function, which was not great. And then you do that, and after a while you say, okay, now I'm going to publish this software, and then, okay, now you have to install this Fortran package that exists since 1990, and it needs a lot of dependencies, so good luck. So you're not really prepared for that. So we're like helping you go from, I just want to work on the solver, so give me the problems, I don't care where they come from, do the thing, here's the output, and generate things nicely. So we talk more about this in other talks, in other JuliaCons and Jump Dev, so you can find more information about all of that. And since optimization is essentially linear algebra and multivariate calculus, we have a lot of packages on those things, either in conjunction with optimization or by itself. So these are our our 6 most famous packages in number of stars. One of them, the most starred one, is Krylov.jl, which is for linear algebra. So it's standalone package, doesn't depend on any optimization thing. And it's pretty well used out there, even by indirectly by SciML. So you possibly use that if you use differential equation solver. And we had a strong research focus. I mean, we have a strong research focus. I'm a research software engineer now in some other field. But the Julia Smooth Optimizers is driven by research, so there are a lot of developments going on. For instance, now we're talking about non-smooth optimization and things using GPU. So if you want to get involved, please check jso.dev. And of course, none of this would be possible without the many contributions that we had over the year. So thanks a lot for all the contributors. Like so many people to count, probably not too many to count, but so many people. Thanks. Just stay a while here just to say thanks to all of you. Specifically, JSO Suite now. So the way that JSO solvers work is you have a model or a problem, depending on the field that you come from, and then you give this model to the solver, and then that solver gives you back an execution stats. So the the provenance of this model or problem is varied. So sometimes you are in the industry and you have AMPL being used. Sometimes you're just an academic doing benchmarks and you have QTIS. So it can be from many places. Or you can just use AD and give a function. So that's why we separated this, so you don't have to worry about model when you're doing your solving. On the other hand, if you just want to solve your problem, you don't want to care too much about the solver, so that's where JSO Suite is coming in. So a model in our field is an optimization problem like this. You want to minimize a nonlinear function. You have nonlinear constraints, sometimes also bounds on your variables. And what you need to make this solvable in our field is derivatives. So you at least want some first order derivatives, but the really good stuff uses second order as well, right? So you want some IP opt, you need the Hessian. So as I mentioned, we are doing this for a long time. So if you want to create an optimization problem right now using one of our packages, you have a lot of options, right? And that's a lot. Like if you want to say to someone, hey, you want to work with us? Here's 50 packages for you to learn, right? But the idea being that there are many ways to create an optimization problem using JSO. And there are many solvers to choose from. Some of these are just wrappers. Some are pure Julia implementations of pretty good nonlinear optimization solvers. And also, there is a linear algebra ecosystem that is not going to be in this talk. But, I mean, we have to give some love to that ecosystem. So where does JSO Suite comes in all of this? Well, JSO Suite is essentially wrapping this part and make it a bit more user-friendly. So instead of worrying specifically about the model provenance and specifically about the solver that you're using, we try to make it easy for you, and we focus on a function called minimize. So minimize in yellow here is JSO Suite. The problem is something from somewhere. We're going to go over some examples, and you just have an output. Optionally, you can give the solver as well, and then you can be precise on your solver requirements. So a few examples on how to use JSO Suite. The first one, the simplest example, many people want to solve this, minimize a function. So I'm going to try to give some motivation for the non-optimizers in the crowd. You have logistic regression, for instance. And this is essentially, I want to find this nice red curve that's going to help me classify the points, separating the 0 ones from the 1. And that is an unconstrained optimization problem. Essentially, you want to minimize a function. So if you have that function, you can just say minimize f. If you give a starting point, things go better. That's a normal rule in the field. So this is the example for that code. So you can see it's not a lot of code to make that work. A lot of Julia things going on. So this is a sigmoid function using if-else. I define the cross-entropy loss, the classifier thing. And this is the objective function, fit obj. So this is the fit method from the classifier. Here I'm just saying it's a sum of the cross-entropy loss. No, the details don't matter. This last part is the fun stuff. You can just say minimize fit obj. Starting point is once, why not? And it works, right? So first example. If you want, you can give the solver. So right now the interface is you give the name of the solver as we have it internally. So if you give the IP opt, it will use the IP opt solver for this problem, which is overkill. If you don't use IP opt, so the normal solver that we have for this is our own implementation of LBFGS. It's a pure Julia implementation. So it handles multiple precision, for instance, right? Another example of nonlinear optimization problem, and we can showcase the largest interface, is a portfolio selection. So you have many stocks and you have money, great for you, by the way, and you want to decide how to invest your money on this portfolio. So 50% on NVIDIA and another 50% on Bitcoin, right? Why not? So this is an optimization problem. In this case, I'm thinking about the Markowitz model, but the main idea is that you have an objective. In this case, you want to minimize your risk while also maximizing your profit. So it's a balance between two things. You have bounds for these values because you're essentially saying how much are you putting in each stock. So it's between 0 and 1. And you have a constraint, which is a function, this constraint and their bounds, which is I'm going to take all of these fractions. It must add up to 1, right? So this is the normal interface for that. And this is the implementation of that problem. So you have the mean and variance, the covariance matrices, and you define this Markey function, which is the Markowitz minimization of the risk, and with some term for the maximization of the returns. But essentially what I want to say is it's functions, and you just give the functions in that order to minimize, and it works. So in this case, since it's a constraint problem, we are using Percival, which is another one of our solvers. One particular thing that people coming from MATLAB ask me a lot is I want to use quadprog. So if you know quadprog, you already had the spoilers for this slide. But the idea being that, well, in that particular case for Markowitz, that is a quadratic problem. So it's specifically the function is quadratic like this, and the constraints can be expressed as a matrix times a vector. So they are linear. So I don't want to actually give a function. I want to just give the values, matrices and vectors. So you also have that interface here for minimize. So minimize and then these things, and it also works. And that's the same example again if you want to copy paste it later from the slides. In that sense, we also extend, so one of the things that we'll study for a bit are nonlinear least squares. So essentially trying to fit a nonlinear function, if you want to think about machine learning. The idea here is that the objective function in this case is the norm of a multi-value function, which you can think about, you can think of as the residual of a problem. So you have the errors of your fitting, okay? So this is essentially minimizing, doing nonlinear regression, trying to minimize the distance for each one of these equations separately. To minimize a problem like this, you can just say, here is my residual function, and you have to inform the number of equations. And this is an example of that. So this is a nonlinear fit. These are all fake values. Don't have any good example ready. So these are fake values. So this is a completely nonlinear model. And it's pretty short to do that. So here is the nonlinear function that is used to fit that stuff. And you can just define your equations using the vector notation in Julia. And it's also just works. Again, this is being solved by JSO solvers internally using one pure Julia implementation of, I think in this case might be a Newton method, second order method. Finally, maybe not finally, but you also have the option of actually using the full abstract NLP model from JSO. So if you do say, I don't want the easy stuff, I don't want just autodiff, I want to control completely how my model behaves. Or for instance, you're doing something with PDE constraint optimization, so you want to use another package of ours, the PDE constraint optimizers, I guess, and then you want to take that, create a optimization problem, and just give to minimize. That also works. Okay, so it's still possible to use the rest of the models, not just the automatic differentiating ones. So one example that for PhD students is pretty relevant is the qtest model. So when you want to do benchmarking, you have this package called qtest. It exists for some years now in one way or another, and we used it to create benchmarks. It has maybe 1,500 problems by now, and it's all Fortran. So this is essentially taking that Fortran code, compiling it, and giving it to you. So if you want to do benchmarking with this, I think has millions of variables in some of them, and you can do benchmarking with that. So it's easy to just go there. And one cool thing that we are hoping to get to all of our packages, but the main ones already accept, are the options that you give to minimize. So so the options are essentially passed to the solver that you use internally. So most of the solvers, the most famous ones, will have these arguments. So ATOL and RTOL for the absolute and relative tolerance. But the cool stuff here is the callback. So if you have the callback function, we're going to call it internally in some of our solvers. And this is an example. This is logistic regression in 2 dimensions with a quadratic function. And I have a callback function here that I have cut because plotting is hard. And it is bound. So this is a simple example, but you can do that, for instance, to control the loss of your machine learning model, for instance, right? Most of all, it's just cool to do as well. So JSO Suite is essentially trying to make your life a little bit easier. So it's user friendliness first. We have shown a few examples where you can just take our various model sources, and you can use many of the optimization solvers, and you just plug those things there, and it works, right? So that's the takeaway of what JSO Suite is for. You can just use it if you want to minimize things, and you don't care so much about like what's going to be used internally. So essentially, if you're an end user and just want to try something fast, so first prototype, you can start with JSO Suite. And that's why we are calling JSO Suite our one-stop solution for optimization. So I hope it helps get more people involved with JSO. If you want to get involved, so our main communication channels are, go check the website. There are some tutorials there. There are news as well when things change, and the communication channels that you can find us with updates will be there. The short version is that we are on the Slack and on Zulip, mostly on the math optimization channel and some other places. And you can find us in the GitHub discussions for JSO. And you can also check my GitHub, my YouTube, Abel Siqueira, like and subscribe. But that's because there are some tutorials in the YouTube as well if you want to get involved in optimization. And that's it for me, so thanks a lot for listening.
Yes, thank you, Abel. Any questions? Yes, quite a few. That gentleman first, and you will be the second.
Yes, sorry. You might have covered this, but I just wanted to confirm that it supports nonlinear constraints as well, right?
Oh, yeah. Yeah, that's the main use case.
Yeah. So the main use case, yeah, okay. And also, do you have like alternative optimization algorithms? For example, I saw you had LFP, BFGS, right? But do you also have, like, example, polyopt that alternates between Atom and BFGS?
What? Which one you said, sorry?
Polyopt. There's like
oh, yeah, okay. Well, we don't have that one. We have many optimization solvers. So the pure Julia ones that we created, we have. We have wrappers for IPOpt. We have a wrapper for Nitro. And we have now a way to communicate with Jump. So if Jump has it, we can use something to use it. It should be easy, so that it should be easy, to also create a new wrapper to use existing solvers. But we are not working on that intensely, so if you want to get involved to do that, we help you get that done.
All right. Oh, and then finally, is it easy to convert objective function from what's it called, differential equations that you let's say you've written one in symbolic notation and use that for your module?
I'm not sure because it does depend on what they do internally, but there is some intersection on how we do things. So for instance, our AD NLP models uses a lot of different backends. So AD NLP models being the thing that computes the automatic differentiation. So I think right now we are using a package by Guillaume, which is sparse connectivity something. I don't remember the name, but it's doing the AD like that. But for instance, we had some investigation with Zygote at some point. So there is some intersection. So I imagine it shouldn't be too hard to connect the two of them.
Okay, thank you.
One, two. So thank you for the talk. Can this support non-differentiable problems and global optimization and so on?
So a great question. So on the non-differentiability, so it is Julia smooth optimizers, but actually there is some work being done right now. So the other creator, Dominique Orban, he is now working with non-smooth optimization. So it might be possible to do something like that. I have zero knowledge of non-smooth, so I don't know. But there are packages, so you can look into that. And on global optimization, nothing. Nothing currently, because it's mostly the idea of being you want to look for a first order optimization, first order point, right? So we don't look so much for the anything that can be provable global, or we don't have multi-start. Multi-start should be possible to implement, but we don't have it implemented. And on other kinds of global optimization like convexity, we are not touching that at all. Thank you. Yes, the question was, have you tested the scale of the problem and the scalability? Kinda, yes. It does depend on which solver, but the Qtest benchmarking includes problems up to millions of variables. I think some of our solvers will struggle with some of the largest ones because they are really large, but also my computer struggles with just loading them, so I can't really benchmark. But yeah, we have tested a few things. The IPOpt solver at least handles those very well, and we are looking for people interested in working into improving some of our solvers as well. That's something.
More question?
Thank you again, Albel,
Thank you.
for the speech. And we will have a launch session at third level. And if you have any questions on the lecturers and speakers are there, you can meet them and catch them, ask questions there as well, if you're interested. Thank you again, and thank you again.
Thank you.
Okay, welcome everybody. We're now starting the last session of whole of JuliaCon. So we welcome Jonathan Taylor from the MIT Lincoln Lab, and please tell us about MagNav.
Yeah, so today I'm going to be talking to you about real-time airborne magnetic navigation with magnav.jl. So we've been coming to JuliaCon for the past 3 or 4 years now, presenting sort of the same subset of software and some data collections we've done over the last few years. This is kind of bringing that all up together and wrapping it up with a nice bow for what we've been trying to do for the last several years. I'm pretty much going to start with what is magnav, because we've kind of realized it's a niche topic and a niche topic because most people don't work in navigation and most people specifically don't work in alternative navigation. Then we'll go through some of the data we've got as well as sort of the approaches that we've been taking. So the core problem we're addressing is GPS denial. As I'm certain most folks here are probably more keenly aware of than back in the States, GPS is kind of trivial to deny, be it any kind of GNSS system. You're kind of seeing this acutely through commercial airfare in Estonia and Finland right now, as well as in the entire Ukraine. It's kind of a very vulnerable technology, and this is sort of also true for BiDAO and the other sort of GNSS systems. However, you do kind of need GNSS to correct any kind of inertial system, which is what you're using moment to moment to navigate. It acts as a way to ensure that your inertial navigation system isn't drifting off into oblivion and assuming that you're in the middle of the ocean when you haven't left Germany yet. There's a lot of other ways of doing this. You could do terrain following, which works great if you have a good map. Visual navigation, which works great if you're doing SLAM and going to be over the same area for quite a while. Signals of opportunity, so if you know what signals are in the area, like Wi-Fi is a great way to do this. You can generally just position off of that. And then celestial navigation, which we've been doing for, I don't know, a couple of millennia, just looking at the stars and trying to figure out what's going on. Each of those, though, have some cases where they're great and a lot of cases where they're awful. Some great examples are like visual navigation when it's cloudy and dark. I don't know what you're looking at. So we're looking at magnav, which is using the Earth's magnetic field, or more specifically, the crustal magnetic anomaly field to navigate. So you're looking at the distributions of ores and other objects within the Earth's crust and measuring the magnetic field due to those components to try and navigate. This is something that's been well explored in sort of the oil and gas industry, because this is the same fundamental process you use if you're, say, doing a geosurvey to try and find oil or natural gas deposits over an area. You effectively have to build the map that we're using in order to find those deposits. Additionally, since magnetic signals, unlike electrical signals, degrade with 1/r cubed, it's kind of difficult to jam this. We did some back-of-the-napkin power calculations at one point, and you kind of have to put a nuclear reactor on a train and follow your plane around to have any kind of perceivable impact on what you're measuring at 30,000 feet or mid-flight. So diving a bit into the magnetic field, I mentioned the core anomaly field, or the crustal anomaly field. That's really just the components due to things like the lithosphere and the mantle, so sort of the upper mantle or the crust regions of the Earth. You do also measure the Earth's core field, which is very well modeled, and the Earth's space weather effects, so what's going on with the sun and other things, which isn't well modeled, but you can normally get around by having a base station somewhere and just measuring the differential off of that. The last thing, and sort of the most important thing from a deployed perspective, is the platform effects. So if you actually break things out by magnitude, the core field is somewhere in the neighborhood of like 30 to 50,000 nanoteslas day to day. So tens of thousands of nanoteslas. Temporal variations or space weather effects are somewhere in the area of like 10. We don't really care about 10 nanoteslas because the crustal anomaly field, or what we're actually using to navigate, is on the order of about 100 nanoteslas of variation. So if you're off by 10, even if you're off by as much as like 30 or 40, you're normally okay, assuming there's still sufficient variation. And then with the platform effects, you kind of end up with a couple of very different cases. If you're on a geosurvey aircraft and you've put your magnetometer on a 3 to 5 meter long boom behind the plane, you're only detecting up to about 10 nanoteslas from the aircraft, which we could ignore. I can't put a 5 meter long boom on an F-16 or on a Boeing 737, well, I mean, it might crash, or on any other kind of commercial airliner. So for those cases, I have to put it in the actual cockpit or the cabin itself, and there I've personally seen as high as about 3,000 nanoteslas of variation in the signal, at which point you have completely lost the anomaly field in the noise. This means that we actually have to do something called platform calibration. And the conventional way of doing this is something called Tolles-Lawson. So 1937 and 1942, a couple of folks, Tolles and Lawson, came up with some approaches for doing this on sort of World War II era aircraft because they were trying to figure out how do you navigate across the ocean. And they were like, well, the magnetic field could be kind of useful for this. As it turns out, they weren't able to put the maps together, so that kind of got binned. And then in 55, they wrote out their equation. And it's really just a quick way of saying, if we look at the aircraft in multiple orientations to the Earth's field, what do we see as far as its magnetic field? Once you have that, if you know your orientation, you then know a couple of the components of your magnetic field and can subtract that off your signal. This doesn't get everything. This is perfect for a geosurvey aircraft. And realistically, with a geosurvey aircraft, you're done at this point. For a jet, there's so many other temporal things that aren't quantified here, like varying electrical signals, lights, the fuel pump, passengers, that you have to do something in addition to this, which is sort of where the rest of our project comes in, and I'll get to that in a second. But if we sort of take a step back and look at what the ConOps looks like, or what the actual application space looks like here, you start with GPS. So we know where we started. We lose GPS at some point, and we continue using INS to navigate. And then while doing that, we measure the Earth's magnetic field, remove the platform effects, and use that to bound where our INS can be stepping to. So we're not eliminating error. We're simply saying the error in the INS will never exceed this value. We're dampening the growth in error to near zero. So taking a high quality INS, damp it to near zero, you can pretty much navigate on that forever in a 50 to 100 meter bubble, and no one's going to care. We don't always need the 1 to 5 meters that GPS guarantees us. So it works. We know it works. We've done it a bunch on a geosurvey aircraft. Like I said, though, this isn't helpful. Sure, it works when everything's on a stick, but we kind of have to figure out what it looks like when we actually go on a plane and put it somewhere else. So to pursue this, we put together a data set where we kitted up a Cessna Globemaster with an additional 4 or 5 magnetometers within the cockpit, some additional voltage sensors, some additional current sensors, just sort of anything we figured could come up with a magnetic signal. We kitted it up with a sensor to see if we could detect it. We made this collection in 2020, put it out publicly so other people could look at it, and have been sort of churning away at it since. And that leads to our year 1 collection where we got about 40 hours of flight data. Now, I can't really emphasize how nice it is to have a 40-hour flight data test set, considering that equivalent data sets that we've seen from like Oxford with their walking data set or a couple of drone-based collections rarely get past about 5 or 10 hours of like good, usable, well-collated tabular data. Whereas here we have fully time-aligned, fully synchronized, well-constructed data at about a 10 hertz sample rate, which is surprisingly nice. And all of this was collected over Ottawa, Canada, in 2 very well-mapped regions. Well, we took that, we turned along, we got that 17-meter number, we were happy, but then we sort of went, well, we're over land, who really cares about this? I mean, you could use visual navigation and get to 5 meters, which has also been done. So we did something silly. We decided to go fly over water and fly over some of the Great Lakes, which are particularly deep for water as well. And we're still working on this data, but we're seeing very similar results over those cases where you can demonstrably show that those other LP&T technologies wouldn't work. Again, all of this publicly available both on the Zenodo page that houses the first year website, as well as through our repository through our package MagNavJL. You can just pull it in, use it, churn away, do whatever you'd like. So all in all, we've got about 80 hours of flight data, fully kitted up Cessna. This is great. If you want to navigate off the tail stinger, you can do that. Learn how to navigate. It's a good old time. However, if you want to start addressing the problem of platform calibration, you start looking at the magnetometers within the cabin itself. And what we've kind of noticed over the years of collection and working with this is that mags 4 and 5, so the ones towards the back of the plane, are what we like to call our easier ones. Mag 5 is very easy. There's very few electrical signals within the plane that go near it. It's on the roof of the cabin at the back of the cabin. Mag 4 is directly below it on the floor, which has some control signals for like the rear rudder as well as some of the lights back there. And then we have our medium or kind of hard magnetometer, with magnetometer 3, which is on the fuel pump, which is where it turns out those voltage and current sensors end up being extremely useful, because you can directly just pull that in and say, this is what the fuel pump is doing, this is the electrical environment there, we can now use that for compensation. And Mag 2 is on the back of the pilot and half unusable because of radios. But using all of this, you can get a pretty good view of what's going on, and that kind of led into this challenge problem that we put together, and we've done for the last several years with sort of rolling admissions, where we ask you to take sort of the minimum number of magnetometers and supplemental sensors that you can, and try to replicate the tail stinger from within the using exclusively information from within the cabin. If you want to see more of that, we've got our challenge problem website at the bottom, and I'll pull these links up again at the end. So to sort of set ourselves up for real time, though, we have to look at offline first. So we've got data, we've got a basic idea of the problem. Now, how do you actually put these two things together and do MagNav sort of on your laptop? We're not in the plane yet. We're still operating in a fully offline fashion. So that's where we came up with last year's topic, which was sort of this knowledge-informed AI infrastructure for magnetic navigation. The core idea is we already know quite a bit about magnetic platform compensation. We know kind of what we need to be looking for, what we need to compute, how we can apply it, and how we can actually take this compensation and get to a navigable signal. So as we did that, we sort of started cleaning up our documentation and trying to make it a bit more clear for everyone else, because when you've stared at a problem for 3 years, you tend to sort of get in your own head. And in the process, we came up with a couple of good ways to explain it, which is that we're really sort of doing a SciML style approach, where we've got this physical model, this pseudo simulation of what the magnetic environment should look like with Toles-Lawson, which is directly based off of trying to compute and determine the eddy currents, the induced fields, and the permanent fields within the plane in a very static fashion. It knows it in regards to attitude and elevation. It does not know it in regards to time. And then we augment that with a neural network trained off of some of the magnetometer readings and some of the supplemental data to actually build out what the transient inferred correction is. So we're not fundamentally building a whole new compensation framework. We're augmenting the currently existing one to sort of make it apply to what we need it to do. And that's to deal with things like radar, cargo, personnel. I mean, we have a whole example on our package that actually walks through how you can detect the direct impacts of a particular strobe light on one of these magnetometers. And it turns out that since the neural network doesn't have to learn about the modeled components, you can get away with a 2 or 3 layer just feed forward network. It doesn't need to be anything too powerful. But that very small network ends up being just about perfect here, and it's helped us avoid what's happened for some of the pure machine learning approaches, where you end up with a 20 or 30 hour training set, a very large RNN, or a couple of transformers, and then it doesn't really transfer well because you've trained on 30 hours on one plane, then you go to a different plane of the same make and model, and it doesn't really work because there's a couple of other particulars there. Whereas in our case, with a small, like 2 to 5 minute transfer function, or if you're training from scratch, about 20 minutes, so just during takeoff proceedings, retrain the network, and then you're good to go. Yes and no. So it depends on what you're... Yes. So he asked if we're training a new neural network for each new airplane. I hate to say it depends, because by airplane here, you can mean same make and model. So like we're talking about all of the Boeing 737s, or we're talking about each particular Boeing 737. In this case, we've looked at what we called a sort of a group model, so all of the 737s, and you can get to decent performance. You do still want to potentially fine-tune or retrain during your takeoff or initial flight, because you want to deal with some of the oddities of that plane. Because sort of some of what I've discovered with a lot of the work on this is that no two aircraft, even if it's the same make and model, are the same. They'll have different software blocks, so they'll be running different interpretations of their own sort of way to manipulate the circuitry, or they'll have different damage they've undergone, different maintenance procedures. You're going to need to fine-tune for any new sort of tail number that you're hopping on. I hope that answered your question. And sort of what I was talking about earlier, this is what it looks like when you blow up that previous diagram into what we're actually doing. So you take Toles-Lawson, you keep it in the vector form, break it out into its individual components, And then you use just this neural network here to build a small additive correction, and you move on with your life. This turns out to be extremely powerful and tends to just work fairly well on its own. As you can sort of see here, where with the individual components, our correction doesn't have to be that big. Toles-Lawson will buy you a lot, especially on a geosurvey aircraft with a sufficiently well-placed magnetometer. But without it, we're dealing with sort of magnetic field errors in the area of 130 to 150 nanoteslas, which is still sort of beyond the bounds of what you can navigate off of. Your error is larger than the actual signal you're trying to use. Once you add in sort of if you just go to a straight up vanilla neural network, just use an RNN, you can get to the 60s, which gets you a pretty good navigation, but it doesn't really transfer well. It doesn't really extrapolate well either. And then when you combine the approaches, so Toles-Lawson and the neural network, in some cases, you do as poorly as 55 nanoteslas. I say you do as poorly as 55 because that's the number we put here because it's sort of the largest magnetic field error that we've seen when you have a well-constructed model. I've built models using this technique that have gotten as low as 9 or 10 nanoteslas, which is eminently navigable. At this point, you're the same as the day-night cycle, and we no longer care. And this has already been released and integrated into MagnFJL, is extremely well documented, and has several Pluto notebooks that can walk you from, I just looked at the data, to I'd like to navigate. So that's sort of offline navigation. We're, at this point, still existing purely in the realm of, if I just handed you the repository and said, have fun, you could probably get here in about an hour. Now we're at real time. Here we have other problems. Here we no longer have all of our data already ingested, already having gone through the communication systems and already arrived at your laptop, fully time synchronized and ready to go. We now have to deal with sample rates. We now have to deal with things like different connection standards. We have to deal with data being synchronized almost, so things potentially arriving out of order. We have to deal with things like altitude variation. There's a lot of other things that show up when you actually try to deploy this versus when you just run it on your computer and take a look. And sort of a lot of this boils down to just really dealing with and digging down into that communication system, where we end up using LCM, so the Lightweight Communication and Marshalling Standard, because as we've kind of found, it's exceptionally common in the aerospace industry, especially in the tooling industry, for people to use these very lightweight communication protocols to try and communicate. Now, of course, using this, you're not going to get everything that we have in the offline data set in that full tabular system. You're going to get the inertial system, both in a processed and unprocessed form. You're going to get GPS, so you know where you are for sure. You have a truth signal of some kind. You'll get the magnetometer, because we directly attached an Ethernet cable. And that's about it. So all those nice, lovely voltage and current sensors we had, we don't really have in the real-time environment. So we kind of have to lean much more heavily on things like more precise attitude estimation, more precise calibration, and really lean on sort of understanding what we knew before to identify other signals that we should bring in. Oh, there we go. So at this point, actually, I'm going to pop out of the slides because things are actually running. If I can get the dashboard to come up. It's not really fair to say I'm running things in real time and then just show you a whole bunch of pre-made GIFs, a whole bunch of pre-made tabulatures and everything else that just says, yeah, we did it in real time. It's a lot more fun to actually do it in real time. So here, in this terminal window over here, which can anyone read that other than me? Okay, well that's good at least. This breaks out all of the individual inertial fields, GPS fields, and sort of what you would need from the magnetometer itself to start feeding into the algorithm. This Maki screen that I have up here is put together by sort of our processor, which acts as a full ingest. So this isn't truly real time in that we're not on a plane, but I am taking a recorded segment of flight and debouncing it to act like those messages are coming in 5 times faster than real time, because we only have 5-ish minutes. And I'll hit go, and then pop back over here. So at this point, thank you. At this point, it's loaded in the actual model. It's looking at sort of ingesting a good initial EKF state, because we're using an extended Kalman filter to build a corrective navigation signal. And then once it gets that, you'll start to see these individual charts start to populate. In fact, you've already seen positions start to populate. It is a little goofy because this is an algorithm designed to run at real time, and we are currently running at 5 times real time. So you'll see some fun start to show up when you realize that it thinks the plane's moving about 5 times as fast as it is. But what you can quickly see is that after an initialization period, sort of once you get past this area of low magnetic variability and start to hit components of the map where you're getting a good magnetic variation, the magnav signal very quickly starts to converge onto the inertial signal for quality and eventually surpasses it because it's no longer drifting as hard as long as you have a good compensation. Now, as I'd sort of alluded to before, we don't have every field that we'd like to have, so our compensation is worse than we'd like it to be. In training and evaluation on this flight leg, when we have the full suite of fields that we normally use, we see a compensation error somewhere in the area of like 22 nanoteslas, which is very good. But when we're actually doing the real-time replay, we're somewhere in the neighborhood of 50 to 60 nanoteslas because we lose some of the current sensors and timing. And timing issues start to become a problem. But I'll have to zoom in here on the nav error. As you can already see, with magnav, we've beaten an exceptionally well-calibrated INS system. We've locked on our confidence ellipse at a good point. Our position errors are very stable, and we're looking at about somewhere in the neighborhood of like 30 meters right now, and by the end of this replay, I think it gets to about 45 meters of navigation accuracy. Now, of course, I say it'll get to 45. It's still a stochastic process, given it's a Kalman filter. So if it does better, no, it's not going to do better than I thought it was. It's going to do about as well as I thought it was going to do. But really, the important thing here is so long as you have a stable calibration, which you can pretty quickly get to with MagnavJL, you can then leverage that with some simple other Julia libraries for message streaming, as well as some of the asynchronous systems within Julia to get to this point where you can do real-time magnav, and I can honestly, actually personally say that I've taken this same set of software and instead of replaying messages, actually hooking it up to a router so it's getting the correct messages from the rest of the hardware, and you can run it mid-flight now. It's not very difficult to sort of change this back over. You really just have to turn the other script off, but you can see very similar navigation errors mid-flight. And there's actually a few companies that we've been working with that are currently trying to get to that point for commercial aviation as well as other things. I think, yeah, I'll stop the replay. Actually, I'll just let it go. I guess at this point, I'll pop back to slides, if slides will come back, and then I'll just sort of ask for any questions, because if it'll let me. Yeah. So, and here I've got our project codebase for MagnavJL. It's also just perfectly available in the package manager. We've got a Docker that has everything instantiated, including the Sanders geophysics data, so the year 1 data, I believe. We have a data set over on Zenodo, and we've got our challenge problem description available for everyone as well. Thank you. Any questions?
Oh, thanks, Jonathan. Yeah, what are your questions?
Thank you very much for a wonderful presentation. Why Julia and not any other software here?
So there's a couple of good reasons for that. Initially, it was because we were trying to build out a simulation system for estimating the magnetic environment within the plane. So Julia was very convenient because we were going to be able to differentiate through sort of our mathematical model of the plane itself. Since then, we found a lot of other computational efficiencies, namely the ease of ability to write sort of your model once and deploy it on a wide variety of architectures. So we've had this running on embedded hardware like a Raspberry Pi up to a supercomputing cluster that has multiple GPUs. So initially, because of some niceties with the auto differentiation system, now because it runs everywhere and I don't really have to think too hard about how I rewrite all of this in Torch such that it can run on both the CPU and the GPU, and I'm not using special functions, and it's just a lot easier. And I do say that going, I'm primarily a Python developer, so I'm not saying that because it's because I know Julia. I know Python much better. It's just a lot easier to do things like this in Julia than it is in Python because of some of the niceties around, especially Flux. Flux and Lux have been beautiful.
If I may ask, do you a lot of the development by yourself? Or
So
how large is your team?
our team is, I can pull it up to here. Really, for the last 2 years or so, it's been these 4 people. So myself, a PhD, well, he's graduated now and then was a postdoc at the Julia Lab, Albert Gannat, Alan Wolber, and Glenn Carl. So a couple of my colleagues, as well as Albert Gannat, have done the majority of the work, including myself. Most of what I've done has been on the real-time translation, project management, which is always great with grants, and then a lot of work early on with helping trying to formulate some of the individual ideas and making sure that we could actually get things working. Cool. Oh.
So did you ever try just running a Kalman filter without your approach to see
Yes.
how it does?
If you run a Kalman filter off of just the inertial navigation system, you're going to see identical results. So when you get to, where are we? Here, if I get, actually, I can just do this. So this blue line you see here is just a Kalman filter running purely off of the inertial navigation values. If you run it off of that plus magnav, it drifts into infinity very, very quickly because you've introduced functionally random noise as a truth signal. You kind of have to do some form of compensation. So tolls Lawson initially, and even then you'll see degradation in sort of navigation relative to our approach because you still have quite a lot of noise. You do really need to get that compensation error under about 100 to see something useful, 50 to see something okay, 10 to see something that's a GPS replacement.
Okay, so it's thought as a GPS replacement or as an addition to GPS?
It is in addition to GPS. This is not going to get you to GPS's aviation promise of 5-meter accuracy. You probably don't need it. Your plane's bigger than 5 meters, but that's what GPS is able to do, especially in its currently deployed form. However, GPS is very easy to jam, whereas this is all internal to whatever vehicle you're flying it on. So even if this only gets you to 50-meter accuracy, at least from what I've seen, for 95% of use cases, that is more than good enough for what people are actually trying to do with GPS.
Okay, thanks to the speaker again. And the next speaker can already come and set up. Okay, let's welcome our second speaker, Angeline, and go.
Sure.
Stage is yours.
Okay, thank you. Well, thank you all for coming to my talk. My name's Angelina Aguinaldo, and I'm a PhD candidate at the University of Maryland, College Park in the Computer Science Department. And I'm also a research staff member at the Johns Hopkins University Applied Physics Lab. And so today I'll be talking about how we use the algebraic Julia ecosystem to tackle problems in robot task planning. So the structure of the talk is as follows. There's going to be 4 parts. The first, I'll begin with a story to try to motivate some of the problems that we see in robot task planning. And then I'll go into the theory of the category theory-based planning language that we are proposing. And we'll be talking about how we implement this planning language using algebraic Julia, and then wrap up the talk. So as you can see here, there's a QR code so that you can follow along, or you can go to this tiny URL, tinyurl.com/planbot. So as I said, I'll be starting with the story. And so this story is about a robot named PlanBot. PlanBot is a robot that has the ability to determine what sequence of actions it needs to take in order to accomplish a plan. And this is typically known as robot task planning. These are finite actions that you draw from a library to determine what sequence in order to accomplish the goal. And so one day, PlanBot decides that it wants to accomplish the task of making a sandwich. So what it needs to do is go to the kitchen and take a look and understand what is in its environment. It needs to know what objects are in the scene, their relations with each other in the scene, and maybe some other attributes about the scene. So the first thing that PlanBot would need to do is take assess the scene using its senses, otherwise known as sensors or image sensors or whatever sensors that you're using in your robotics. And what it will come out to is just maybe some matrix of numbers or whatever sensing protocol you're using, some version of that. And so thanks to the last 10 years of computer vision research, we are getting closer to a position where we can take these computer vision outputs or these vision sensor inputs and produce some sort of symbolic representation of the world. And so what you can see here is that PlanBot is able to understand the world in terms of a list of facts. It knows that there's an object called lettuce slice. It knows that that object is clear and it's on the table. There are also a few other objects, such as a tomato slice. Let's see what else. We have a plate, we have a knife, and we have a couple of bread slices. And all of these items also have associated attributes, such as the mass, or the temperature, or the material. And as I mentioned before, some facts about the relations of that item relative to the world. So if it's on the table, or if it's clear, and so forth. So now that PlanBot can see the world in terms of these symbolic facts, it's now in a position to ask, what's the plan? So typically, PlanBot would need to do a couple of things in order to actually compute a plan using this representation. And as you saw in the world representation, the facts seem to be according to some structure or predefined language. And this language is determined by these predicate templates. So you can see here we have some predicates, such as object, receptacle, tomato slice, some of the things we've seen already. But then there's other predicates, such as the temperature and mass, as well as predicates that involve two symbols, like is part of or on one another. So on one thing is on another. And these templates serve as a way to structure our representation of the world, as well as our action models. And this syntax is clearly not Julia. It's actually in the form of the Planning Domain Definition Language, otherwise known as PDDL. This is the most commonly used representation language for robot task planning, and it goes even beyond applications beyond robotics. So as I said, we can structure the world using these predicates, and we can also structure our actions. So as I mentioned before, robot task planning involves drawing from a list of action or a finite set of action models and determining what sequence to apply them. So let's say that PlanBot has in its action model the notion of a stack action. The stack action has couple of parameters, or two parameters. It also has a precondition, and it also has an effect. And so what happens in the algorithm is that it needs to take this action, take a look at all its preconditions, and then compare the preconditions, every or predicate statement within the precondition, against the world state. So what it would need to do is say, let me find a fact that resembles the symbol of clear and some symbol. So clear and lettuce slice it can find, and then it could match it against holding bread slice. And so once we've identified a match within our world state, we can then go to the next step and apply the action. And so to apply the action, what we need to do is take a look at what is the instructions provided in the effect. So the effect has a set of predicates. Here there are 5. 3 of them do not have a not in front of them, and if it has a not in front of it, it means we are deleting that predicate from the world state. So in this case, we can see that the effect of this action has inserted the predicate of arm empty within the world state. It also is inserted the predicate about the bread slice being on the lettuce slice, and it also included the clear predicate, which means that the bread slice is clear of any object. If you had noticed, it actually also deleted 2 facts, which is the fact that something is, the under object is clear, and that the object that PlanBot was originally holding is now not being held. So what needs to be done after in most planning algorithms, after every action is applied, we're checking whether the goal has some inclusion within the world state. So what that would mean is that we would need to see if there are symbols that are included in the world state that are contained within our goal. So from the left, we can see that the goal is to create a tomato and lettuce sandwich on a plate. And there are a couple of predicates, things being objects, those objects being of some type of ingredient, and then those ingredients being stacked in a certain configuration. So this world state can be, each one of these predicates can be checked for inclusion within the world state. And we can see that most of the predicates are satisfied, and let's assume that the rest of them are. If we assume that the rest of them are, then we can conclude our planning and move on with our day, and PlanBot can return a plan. However, there's an implicit assumption here that has been underlying all along, which is the fact that a certain object can only be one type of ingredient, for example. So I said that our bread slice is a bread slice has a symbol bread slice 1. It also can be an object, but there's nothing really prohibiting it from being a tomato slice. Bread slice 1 is just a symbol, and it can easily and as likely kind of be expressed as tomato slice, bread slice 1. And so we have a discrepancy in the world state, and this causes a problem in planning because we have no way of enforcing this representation to have other conditions imposed. So that kind of brings us to the problems with task planning, or at least a subset of problems that are within task planning. The first of which is you may have noticed that the predicates since they're used to structure the world state, if you have many predicates, the state can become very expressive. And that means that when we are looking to apply the action, it may take some time in order to compute the match. So if the world state has many facts about it, then we have to iterate through all of them and determine the match, and that would cause a increased branch factor throughout the search space and result in a combinatorial explosion. It can also be seen that the PlanBot wanted to have the world state be according to some implicit structure. PlanBot is assuming that every object is one type of ingredient, bread slice, tomato slice, or even a utensil. It can only be a plate. It cannot be any other thing. But those things can't be easily embedded within the representation language we're using. So it's looking for something else. And then lastly is someone might argue that you can create an action model where you add into its effects the fact that if you only want to pick up a lettuce slice, then the thing you're picking up can must not be any other thing, and kind of include that in the action model. But that would be cumbersome, and you'd have to create actions for every kind of combination. So it's desirable to have these things be made generically. Okay, so now that we've sufficiently anthropomorphized our computers, we can move on to talking about our approach, which aims to tackle some of these problems. And I'll begin with the theory and then talk about how we implement such things in algebraic Julia. So the main concept of our approach is the fact that the actions, instead of being these preconditions and effects, which are sets of predicates, are now a triplet of structures. And these structures are what's called functors, which I will describe in a little bit. But the top row here is describing the action model or action rule. And all the way to your left is the precondition, which includes a shape or a structure that will match within the initial state. And then to your right, there's an effect, which consists of another structure that we will be using to replace what we've matched in the precondition. There's a thing in the middle, which is different from the existing representation, which is the glue. And the glue matches identifies structures within the precondition and effect that remain consistent. So that just kind of tells us what is preserved throughout the update process. So the precondition you can see here has a square and a triangle and a circle. And that circle is then replaced by a yellow trapezoid in the effect. And so when we we can find a match in the initial state with this precondition, you can see the pattern appearing below. And once we've computed what's called a double pushout, to the bottom right is the resulting state. It is a same state, except the circle is now replaced with a yellow trapezoid. So the magic of all of this comes in the fact that the action rules and the pushouts are what's called, are within the category called C set with a big S. So I'm going to tell you a little bit about that. Before I go into the category of C set, we must first talk about a C set, little s set. A C set is a functor from C to set. C is often referred to as the schema category, and set is a category whose objects are sets and whose morphisms are function maps. So we can see an example of a C set. It can store various data elements, but for one, it can store data about people's favorite pets. To the left, you can see that there's a schema, which is a person pointing to animal, and that arrow or morphism is called favorite pet, and it is assigned to some items within the category of set. So person is assigned to the set Sam Molly, and animal is assigned to the set dog cat, and favorite person is assigned to a function that sends Molly to dog and Sam to cat. So this data structure effectively encodes the fact that Sam's favorite pet is a cat and Molly's favorite pet is a dog. Another fun fact about this particular structure is that with what's called a category of elements construction, it is interoperable with the RDF syntax for knowledge graphs. So if we can represent our world in terms of a knowledge graph consisting of triplets, then we can also represent this in terms of C-sets. So I said that a C-set is a functor. And functor is what gives us the structure that we are wishing to impose onto the world state when we instantiate new data. So a functor is some mapping between two categories. Categories have objects and morphisms between them. So as we saw in C and set, those had objects and morphisms. In the case of set, the objects were sets and the morphisms were functions. So then a functor is a map from one category to another such that it preserves paths. So if there's a path in C, then that path or some version of that path will be preserved within D. So let's say that we have a path from X to Z, then the corresponding objects within D will also have a morphism or arrow between them. It can consist of the same number of morphisms or it can consist of just one. But the point is the fact that when X and Z are assigned by the functor, there's a corresponding pathway to morphisms that exist within the source category. Another important thing is the fact that functors, there can be maps between functors, and these are termed natural transformations in the field of category theory. And so this just gives us instructions on how to map the two functors together. So in the case of natural transformations, the functors have to abide by the same signature. They have to go between the same two categories. And so the natural transformation just provides a map from one functor to another, which is a map from the image under the first functor in the target category to the image under the second functor. So the main point about this is that functors impose structure to our representation, and natural transformations can be defined between functors. So now we can move on to the category of C-set. So we talked about C-set with a little s. And now a C-set is a category whose objects are C-set functors and whose morphisms are natural transformations. And something called a span in C-set is a diagram that takes the shape of 3 objects and 2 arrows pointing out of it. And so this span forms the kind of pattern within C-set that we can use to describe action models. And then the last thing about this, which is more of a technical point of the implementation, is the fact that spans are presented as a colimit of representable functors. It's a technical jargon term, but what it just implies is that any related structure or connected structure to the identified objects in the action model are also included in that structure. So let's look at this example. Let's say in our in our category C for this action, we have a heart connected to the square just within the schema. Even though we did not talk about the heart in the action model, that still exists within the action model implicitly. So all of that implicit structure is included within the action model. So when we go to do the matching, it also matches for that extended structure and not just the explicit structure defined. So this allows us to kind of encode and capture some implicit preconditions and effects without having to explicitly state them within the action. Okay. So now we can move on to using algebraic Julia. Algebraic Julia is a package that supports many of these structures. Actually, in fact, it's an ecosystem. It consists of a variety of packages. And I'll talk a little bit about what those are later on. But I just want to show you some of the syntax. So we can define a schema using the @present macro. And we can define objects and morphisms, as you can see here, as well as a pattern for relations. So the objects, in its kind of graphical form, you can see to the right, there are 5 objects and 4 morphisms. And then there is this pattern of relation. So this is important because I mentioned that the semantics or the kind of target category of C-set is set, and that means the morphisms are functions. And so that means that we can't describe relations within this view. We have to kind of impose functions on the morphisms. So that means we have to come up with a different way of describing relations, and that's through the use of this pattern. So the in-on object serves as a relation, and there are 2 morphisms, one pointing to the left of the relation and one pointing to the right of the relation. So that's just something to note here. So once we've described the schema, we can now instantiate some data according to it. So in order to do this, we can use what's called the @colim macro. And this gives us a way to kind of assign symbols to instances of data that are aligned with our objects and morphisms. So as we can see here, we can instantiate a scene that has a countertop and a stool. And it can also have a bread loaf and 3 bread slices. And so we also want to say, for example, that the three bread slices are part of a bread loaf, brand Nature's Own. It's American brand. And also the fact that the bread loaf is on the countertop. We can do that through the relation. And then we can also say, kind of assigning each of these objects to some abstract thing for the sake of, to respect to the schema. So what you see on the right is the kind of Atchit instantiation of this data. And so if we look at the names of the morphisms, G, H, and L, and what they're supposed to map to, bread loaf, the G morphism maps bread loaf to the index of thing. The H morphism maps the countertop to some other index within thing. And then the L morphism maps stool to some index within thing. So if you look to the right, you can look at each of these tables and see that the bread loaf, for example, is assigned to thing number 2. Countertop is assigned to thing number 1. And stool is assigned to thing number 3. So when we look at the relation, we can follow the same idea, and see that the left part of the relation is index 2 within thing. So that means we're pointing to the bread loaf. And the right part of the relation is pointing to index 1 of thing, which means we're pointing to the countertop. So we've encoded the fact that the bread loaf is on the countertop. So now that we have something, now that we have a world state, we can also define a rewrite rule that makes some sort of update to this. And so the rewrite rule consists of the 3 parts that I showed you in the graphical depiction of the rewrite rule. It consists of some data about some arbitrary things, thing 1 and thing 2, some arbitrary bread loaf and countertop and stool. And then it consists of a structure about what is on top of another. So we have the structure of the bread loaf being on the countertop. And these are parametric in the sense that they're not referring to specific items within the current world state. They're kind of just patterns. So the pattern we're looking for is the fact that the bread loaf is on the countertop. That is the precondition, or the left part of the rule, which is indicated by L. And then we have the right part of the rule, or the effect, which has all the same information except for the fact that the bread loaf is now on the stool. So we can apply this rule by computing a double pushout, and what would result is a new world state. What we can see here, we can kind of follow the same thing that we did 2 slides ago, and follow the kind of indices that we're pointing to within thing for each of these items. And we can have, we can see that bread loaf is in thing 1, stool is thing 2, and countertop is thing 3. So then the relation that we currently have states that the bread loaf is on the stool. It's not very dramatic, the change, but the point is that we can, if we are kind of fixing ourselves, or we're ensuring and validating that we're adhering to the structure of the schema with every update that we make to the world. So it's likely the fact that we won't run into a discrepancy when we try to do world state updates, and it would make things a lot more valid. Okay, so just to wrap up, I mentioned a couple of things. I mentioned algebraic Julia, and algebraic Julia consists of many packages. I'm just highlighting 4 here, and those are the ones used to describe or used to implement some of the code that you saw above. So if you're following along on your computer, you can click each of these boxes and kind of direct to the package. Okay, and then the last thing I want to mention is why Julia for this work. There are a couple of features that we've used for Julia, or we've made extensive use of within Julia, but it's not all of the features, or it's not an extensive list. The first is the metaprogramming. As you saw, we used a lot of macros to describe a DSL that aligns with our category theory framework. We also use multiple dispatch quite extensively, particularly the CSET implementation initially was implemented to only instantiate static data, but we've migrated things in order to support dynamic instantiations of data. So that means we don't need to kind of instantiate all of the data up front first. We can add data to our CSETs. And the last thing is that it's fast. The morphism search to do the matching between structures is very computationally intensive, and it's frequently invoked. So it's very important that the language that we're using is fast. So this is just a summary of the work. Before I get kicked off the stage here, I just want to make sure I throw up the contributors and collaborators that we've had. So all of this work is thanks to the support of all the work of other people as well. Okay, thank you.
Thank you, Angela. So you're probably open to answer some questions?
Oh, yes, of course. Open to answering questions.
I do have a question myself. So it's very cool to see yet another planning work actually at Julia. I wasn't expecting this. I'm not quite sure what you get from this category theory modeling approach in comparison to just modeling as an ontology. I mean, you even showed the ontology and the knowledge graph and whatnot. And second question, like PDDL and solvers for PDDL are incredibly fast. Does this, like, if you just ground it out and like if you just model everything and just still solve it, is it still, is your approach really faster also in this case?
Yeah, it's a reasonable experiment and benchmark. We haven't done that full comparison, the PDDL, into this work. I would say that the benefit to using the categorical structure, however, is the validation piece that you don't. So ontologies, you can describe an ontology, but you don't. When you create instances of the ontology, they're not necessarily validated according to some mathematical theory, suppose. So it would be, I think that the benefit is that you can kind of describe formal semantics for all of the ways that you would want to instantiate the world. Does that answer your question?
Yeah.
We can talk more if you'd like, yeah.
Any more questions?
If not, then thanks the speaker again. There's a 10-minute break now, so you can have a walk. And after this, we will continue. Thank you. Okay, we continue. And next up, we have Ray Kimmerer from the MIT Julia Lab. Welcome.
Thank you very much. I'm sure you've all heard enough from me today and the past couple of days. So to be quite honest, this talk won't be super long, and I'll be using some old slides, but I will sort of try and verbally update them for this community and for sort of the past couple months of work. I was introduced, my name is Ray. I'm from the MIT Julia Lab, and what I mostly work on is sparse linear algebra. So the title slide talks about GraphBLAS, and I'll give a brief background about what GraphBLAS actually is. So it's a specification for building graph algorithms using linear algebra. I'm sure many people are aware of the well-known matrix graph duality. You can treat a graph as an adjacency matrix or an incidence matrix or several other sort of mathematical structures that are amenable to computation on modern devices. Like I mentioned, it's a specification, and it's specifically for the common things like matrix vector multiplication, but using arbitrary semi-ring operators. A semi-ring is the most common semi-ring that we all interact with every day is the real semi-ring, the plus and times operators. So when you perform a matrix multiplication, if you think about the very innermost part of the loop, you perform multiplication between one matrix and the other matrix, two indices, in those matrices, and then you sum up a bunch of values, right? You can replace those operations with other operations that fulfill the same sort of requirements of a semi-ring. And that is the crux of the GraphBLAS specification. The specification is a C API specification, a C++ specification, and a math specification. I personally work the most on the C API specification and the math specification, although the math and the C++ committees are essentially the same. And we have two major reference implementations, but the most particularly good one is the sweet sparse implementation. Is the sweet sparse one from Tim Davis, who gave a keynote last year and is one of my mentors and a fantastic software developer and probably the most famous sparse software engineer. Just a brief overview of the state of sparse arrays in Julia. So there's the sparse array standard library. It's relatively old now. It was created in the very early days of Julia. And it is single-threaded and will remain single-threaded until the illusionary Julia 2.0. It's CSC only, at least for right now, and it uses the sweet sparse solvers, which are, as I mentioned, developed by Tim Davis. We have sweet sparse GraphBLAS, something that I have worked on in the past and continue to work on, and this talk is sort of the evolution of that as part of my research. It's a wrapper over GraphBLAS. It's fully functional, and it's fastest for the built-in types that come with the library. We also have Finch. Unfortunately, Willow Ahrens couldn't be here today. She's a sort of colleague at MIT, a fantastic researcher. I believe she's about to graduate. And she has developed a sparse compiler in Julia that is really fantastic and really unique. It supports a ton of different diverse formats you might not think of as sparse, things like run length encoding, which is something commonly used in image formats. And it fuses larger algorithms very heavily. We also have access to hardware vendor libraries like QSparse, RockSparse, MKL. These are sometimes pretty fast. Sometimes they are, to be quite honest, what's the word I'm looking for? They're just there to check a box from corporate, right? So many of these things are there to say, we have implemented this thing on our hardware, but they aren't particularly performant and are oftentimes just copied code from another library with the correct license. And there's also a ton of various smaller packages and interfaces to foreign libraries that I'm neglecting to mention here for time, and I don't know the whole ecosystem like the back of my hand. So I mentioned I had worked on sweet sparse GraphBLAS.jl, and so more recently I have sort of begun to rename this. It's not released yet, but into GraphBLAS.jl for a variety of reasons. And the goal is a unified package for sparse computation for both scientists, graph users, and some amount of ML and AI domains. And the goal is a good balance of user-friendly semantics and optimization-friendly semantics, because those are oftentimes two separate Venn diagrams, right? Some of the design goals here for the front end, the biggest design goal is that you may have any value as the sort of default value. When you think about a sparse array in Julia, the default value is 0. It is always 0. You can't really edit that without breaking the library in a lot of really nasty ways. We want to change that, or I want to change that, because there's many times where you want it to be -1. For graph algorithms, you want it to be sort of this vague nothing, right? Because graph algorithms often operate with these semi-rings that I mentioned before, where you want to swap the semi-ring in and out. So you should just sort of treat the missing value as this thing that works with the semi-ring, but you don't really care what it is. We want to support, I want to support the common linear algebra interface, so matrix multiplication, that kind of stuff, as well as iterators, which is a very important part that I probably won't talk about much here. Executors, which isn't really a common thing that we talk about much in the Julia ecosystem, but if you have ever encountered kernel abstractions supports executors. So you can say, I would like to run this kernel on a GPU, the specific GPU, like AMD GPU, or the CPU. And gradual specialization, which is something I'll talk about in a bit. The other thing is extensibility, the ability to register kernels with the sort of the runtime of the library. So we have these great compilers. Taco also came out of MIT. We have Finch, which is already kind of integrated with my work. But oftentimes, as in real life, as in the rest of software development, the programmer still knows better than a compiler. This is especially true when you have access to sort of the art of someone like Tim Davis, who has spent his entire life doing something like this. And so a lot of compilers, you're stuck with the compiler output. But graphblaws.jl should and will support the ability to register kernels that you know are performant and give them a cost. So I can say, hey, I know the cost of this algorithm given this input, and the compiler will be able to figure out within some reason when it should switch to the handwritten implementation. I'll sort of skip across a few things here. One of the big ones is a sort of unified IR. So one big thing that we've encountered in the sparse world is that in progressive lowering from a high-level representation like matrix multiplication down to loops, you often realize once you've gotten down to the loops that you've made the wrong decision, right? And so recent work from a large number of research groups on something known as eGraphs can help us to lower our high-level representation of linear algebra down into loops or kernels or that kind of thing without losing the ability to say, oops, I made a mistake, I'd like to switch over to a different representation. And then non-destructive optimization rewrites is essentially what I was just talking about. Gradual specialization is something that I think Julia is really powerful for in this space. And to be specific about what I'm talking about is sparse algorithms are typically only performant on a specific format. So CSC, that's compressed sparse column, compressed sparse row, hypersparse, run length encoding, like I mentioned. And algorithms must be changed in order to suit those formats. And even more importantly, perhaps, is that the user must select the correct format. And that is often incredibly difficult for the user. Working in an HPC setting, this is, most users just go with the default, the most easily accessible thing, and that is oftentimes too slow for the experiments that they really want to run. So the goal is, and something that is actually working quite well already, is that initially when you're first running your experiments, you say, I allow the library to choose what format it would like to use. And that is one of the key parts of GraphBlaws, is that the library should be able to decide exactly what structure to use. And then as you sort of hone in on how your data looks and how your algorithm will end up performing, you can say, I would now like to select this exact format. Please, please use this format. And that sort of gradual specialization is the key to the sort of user interface of GraphBLAS.jl. So I have some early experiments in high-level fusion. I think my slides are a little bit out of order here. Let's see. This is fine. So the new structure in GraphBLAS.jl I call a lazy matrix. It is specializable on a lot of parameters, which sometimes can thrash the compiler a little bit, to be honest. And another big thing is that arrays in GraphBLAS are immutable, at least in this library. So you cannot insert into them, at least in this innermost storage that I labeled as immutable. However, you can insert into the matrix at a high level. What happens instead of as sparsearrays.jl does, where it every time you insert, it does a bunch of work in order to insert into a sparse matrix. Instead, insertions are cached for future insertion into the actual sparse data structure. And that can be done very quickly at runtime of a more complicated algorithm like matrix multiplication. I don't know what slide. So the laziness of this sort of array type is incredibly important for capturing algorithms. The current setup captures a very coarse high-level operation graph, including things like matrix multiplication, map, union, intersection, things like that. This graph can also be captured by function annotation, so I can say capture this function definition, and it does the same thing. Execution is pull-based, so what that means is that if I create a bunch of matrices and do a bunch of operations on them, nothing will happen until I read from one of those matrices. That allows us to create the largest possible HLO graph, and it allows us to also try and detect some loops, although that is typically best done with function annotation. Operators and operations are currently really greedily fused. That can actually be problematic in some cases. One of the sort of most basic computations that I have been benchmarking on is fusion of complex conjugate into matrix multiplication, and I'll sort of show some benchmarks at the end of this slide deck at least. Let's see. Yeah, fusion and rewrites are non-destructive, as I mentioned earlier, so that we can decide to do something differently late in the optimization project. And the current supported executors are Finch, the sparse compiler I mentioned earlier, sweet sparse GraphBLAS, and BLAS for dense computations that happen to be caught by the runtime. One of the most sort of concrete parts of the project has been cross-language JIT fusion. So the library I mentioned earlier a second ago, sweet sparse GraphBLAS, is a very complex library, over 200,000 lines of code written by Tim Davis. And that is something that is very difficult to port, even though it would probably be a little bit shorter written in Julia. But he does support something kind of unique, which is that you can give him C code, and he will JIT it using your system compiler at runtime. With some caching that works questionably well. Instead of doing that, what we do is in Julia is we can sort of bypass some of the steps here. So instead of generating C code based on your Julia definitions, I generate LLVMIR, and then this is LTO'd into those same function skeletons I just mentioned using Clang. So essentially we are compiling Julia, small Julia functions similar to those found in like CUDA kernels. So you can't necessarily use garbage collection very easily. Directly into large, very large C code complexes. These can be fairly arbitrarily complex Julia functions with the usual static compilation issues that we all know and love. And then this LTO is actually incredibly performant. We can in many cases, beat or match the C implementations of the equivalent code due to various things that Julia knows that maybe the C compiler doesn't. there are still some issues. We don't have all the same keywords that C does with regard to certain very specific memory optimizations. So there are still some issues, but this actually works remarkably well. Just as a benchmark, relative to the built-in operators, it's a relatively difficult graph to explain, but you can think of this is speed up, so the higher is better, and this is complex conjugate. So there is no complex conjugate in GraphBLAS because it is targeted towards graph algorithms. But I would like the sort of GraphBLAS backend to be usable by scientists, and so we fuse the complex conjugate into the matrix multiplication as you would expect, and compared to just doing this manually, we get over 2 times speed up. And it's incredibly important that we do this with the compilation that I mentioned earlier, because you can see the orange bars are the function pointer version of this, where we don't do any compilation, we just pass a function pointer, and it is actually slower than not fusing. So that's the end of that slide deck. And let's see, one moment here. I will also, for lack of a better thing to do, present some of the work on the next version of GraphBLAS, the API. So let's see here. Where's my mouse? Anybody see it? There it is. Am I there? There we go. Thank you. So I mentioned briefly at the beginning that I work on the C and math specs as well for the GraphBLAS project. And so I recently presented about the next version of the C specification. I've already given this background, so I hopefully don't need to give it again, although please talk to me if I was too quickly, if I spoke too quickly or I glossed over some important details for you. So this equation at the top is actually sort of the key part of GraphBLAS. It's the matrix multiplication algorithm. If you can see, it may not be too visible, but this, it's called the O times function and the O plus function. Those are the semi-ring functions that I mentioned before. And the first thing that we were doing is we were developing a new math spec, so a math-first approach to specification development. We wanted to define all the mathematics in a language-agnostic manner, so that if you pull up C++, C, Julia, Go, there are a couple other implementations, I believe one in Rust, that you essentially know what you're looking at, just like you do when you pull up the dense BLAS, right? The specification is pretty well understood, and the math is very well understood. We also want to reduce the complexity of downstream specifications. So if I write a specification for Rust, I don't want to have to re-explain math for the Rust specification. And implementations can comply with the math spec without complying with a language spec. So GraphBLAS.jl, for instance, will have no specification for it, but it will comply with the mathematical specification of GraphBLAS. This part of the talk will be sort of arcane, so I'll give it a little quickly. We don't currently have the ability to access indices during binary operations. This is important if you're familiar with automatic differentiation. If you want to perform AD on sparse storage with the tropical semi-ring. So if you're performing a reduction with minimum or maximum, you need to know where your value came from in the list of values. And so this is currently inexpressible in GraphBLAS. Another limitation that we enjoy the benefits of in Julia is broadcasting, something that is not present in the current specification and which causes you to allocate a lot of memory, more memory than you should. And then lazy execution is a really big one that we're discussing as a committee, because lazy execution is really hard when you cross language barriers. So if we have a lazy execution engine in C, how do I tell the engine that I have finished executing so that it can perform its optimizations and run the DAG that it has formed? How do I tell it which objects I really need after the after the tree or the DAG has been optimized away. And so that's a really complicated interface problem that not a lot of libraries have ever solved. And we hope to solve this problem so that the implementers of GraphBLAS can make things very performant, because fusion is important in the dense world of scientific libraries, but it is virtually impossible to get away with without it in the sparse world. And finally, we are sort of trying to expand the scope of GraphBLAS a little bit because of an issue that I'm sure you're all aware of, that hardware vendors and software developers can only implement so many libraries, right? If a hardware vendor like NVIDIA has to implement 30 scientific libraries for a big HPC community or a big cluster, they're simply not going to implement all of them, right? Or they're going to implement them very poorly, as I think I mentioned at the beginning. So we want to try and expand the scope of GraphBLAS just a little bit so that we cover more use cases and it's easier for vendors to justify working on this project. So we have 3 new targets: SparseBLAS, which has been recently revived in the scientific community through work at ICL, I believe at University of Tennessee. Machine learning, so especially rank 3+ arrays are very important and something we want to target a lot, as well as more things that may be more unfamiliar, like quantization. And then a large amount of work has already gone into distributed sparse arrays, and that is something we will be specifying in the near future. And I think that is all I intend to talk about today. So I apologize for the sort of brevity of the talk and the old slides, because I'm sure you're aware I've been a little busy. So thank you.
Thank you, Ray. Okay, now this is the time to ask questions.
Hi, thanks, Ray. Do you think there would be an interest in a sort of graphs-like upper layer to GraphBLAS.jl that defines standard graph algorithms like BFS and stuff like that in a more accessible manner, like hiding the semi-rings from the user, essentially?
Yeah, definitely. And so there's prior work in this area. There's a Network X backend written in GraphBLAS, that is much more performant than default Network X. I should also say Tim Davis is nearing completion of a CUDA backend, which will probably be much more performant than in partnership with NVIDIA, but much more performant than cuSparse is today. And so there's already a Network X backend, and there's also a project known as LA Graph. It is a linear algebra graph or something like that, which is also produced by our specification committees. And that is essentially exactly what you're talking about. Rather than worrying about the semi-rings and the mathematics, you have the common algorithms like triangle centrality and BFS and essentially all the Network X algorithms or graphs.jl algorithms you're familiar with.
I'd be thrilled to discuss that with you.
Yeah, definitely.
Hi, thanks for the talk. Tim Davis used to have a old introduction to sparse linear algebra course. Do you know of any efforts to bring that to Julia?
No. So one effort I am aware of is the production of, funded by NumFocus actually, is the production of some videos explaining GraphBLAS in a very sort of 3 blue, 1 brown, Manem kind of way. And I think that will, those videos will map directly onto Julia's, GraphBLAS implementations. So that I think will provide a fantastic introduction for people who are not directly writing sparse codes, which is something most people shouldn't do, to be totally honest. Me neither, because they are very performance sensitive. And that's why Tim Davis is, the one person who writes them all the time. If you've used a linear solver for sparse arrays, other than iterative ones, you've used one of his, and there's a reason for that. In terms of producing content based in Julia, I have discussed the idea of producing some of this content with Tim, and so if I spend less time on this conference, then you may see that in the future.
There's definitely a lot of methods to optimize linear algebra, especially considering structure. So a normal person can't really know all this theory, and so there comes the idea of automation and auto-tuning of an algorithm. So what can you tell us about auto-tuning and stuff like that?
So there's a bit of prior art from MIT and Stanford on auto-tuning sparse compilers. There's not a lot of it. I will say the fastest algorithms, as I mentioned before, are still hand-tuned by Tim Davis within an inch of their life. Like these are massive poly algorithms that are very, very precise with how they do this. But I will also say that they fail in a lot of edge cases because an individual human can't do all this tuning. So there's some work on Bayesian auto-tuning, I believe, in the sparse world. And I believe there are sparse compilers that exist with some limitations in the Apache TVM world. And they have very strong auto-tuning infrastructure in the TVM world. So if you're interested in that kind of thing, I would look there. In terms of the Julia side, I think that is not something I've thought about quite yet. It would be interesting, but it's, that's a whole nother project on top of a compiler, right, as an auto-tuner. So it's interesting, and there's definitely a lot of prior art, but not something I've explored in Julia at least yet. I believe Willow Ahrens, who I mentioned before, works in Julia and wrote Finch, has explored auto-tuning of the Taco sparse compiler, but I'll have to triple check.
Okay, then thanks, Ray, again.
Thank you.
And for now, this time for real, there's a 10-minute break. Okay. Okay, the last sprint starts with a series of lightning talks, and the first one is by Philip.
Thank you. Hi, I'm Philip Alday. I'm presenting my package today, boxcox.jl. It's a lightweight package with nice extensions, is my claim. It implements something called the boxcox transformation, which is a way to kind of get normality in a distribution. So it looks at the set of possible power transformations, and it tries to propose a way for you to get your data to be more normal. This is, of course, very useful in linear regression. I'm not going to go into the math here, but it also will give you the log as a special case. As an example, this is a normal distribution that I have squared, and you can see that the square of a normal distribution is indeed not normal. And with boxcox.jl, you can just fit the boxcox transformation, and it will give you an estimate of this. It doesn't come back as 0.5 exactly. That's life with real data. But it does this, and it uses kind of the stats API fit syntax. This is where we start seeing kind of the nice extensions that I was talking about. There's a Mach-E extension, and so then you can use boxcox plot, which actually plots the likelihood profile for the transformation. And so you can see what values are used. And so you can see that the maximum is achieved at around 0.2 and change, but there's also a 95% confidence interval on this. This is very comparable to boxcox and our package MASS. And so if you have an appropriate Mach-E backend, you can do this. And we can also fit it and apply the transformation. You can see that the returned object is a callable object, and so you can broadcast it, and then wham, bam, you have your transformed data. Very easy. More interesting is that you often want to do this for linear regression of some type, and so you want to look at conditional distributions. And you can do this quite simply. This is, again, an example I borrowed from the R world, looking at tree data. It's growth, height, and volume of trees. And the best model that they discovered empirically is that basically you log transform all these things. So I very cautiously constructed a model matrix with an intercept log transforming the height and girth, and use that to predict the volume of the tree. And what you see with the diagnostic plot is that you get an empirical estimate of negative 0.1, but 0.0, so the log case is well within the 95% confidence interval. And so that's actually what we'd use in practice. We wouldn't choose the MLE here. We just use the one that actually fits well scientifically, bringing in some expert knowledge. But this is kind of annoying to build your own model matrix, and we have a nice package for that in Julia, statsmodels.jl. And so if you've loaded stats models either directly or because you have glm.jl loaded or you have mixedmodels.jl loaded, you can use the formula syntax. And you don't pay a cost for this because, again, it's a package extension. So if you're not using stats models, you don't pay a cost. But if you are, you get this nice little treat. This also works for mixed models, which is something that the R universe only very recently got. I think they took the gauntlet being thrown down. So this is a mixed effects model looking at reaction time and sleep study. Test subjects were deprived of sleep, and their reaction time went down the longer they went without sleep, unsurprisingly. If you actually fit the regression model here, there's a couple little problems. But what we can do is we can fit the regression, we can fit the boxcox transformation, and again, we just call fit boxcox transformation, and then we pass it the mixed model we started off with. And it fits it, does it relatively quickly. Again, this is a package extension, so you don't pay the cost if you don't have it, but if you do have it, great. And again, kind of highlighting something empirical about this is that time minus, so the inverse of time has a natural interpretation of speed. It's well within the 95% confidence interval, so rather than using the empirical estimate of minus 1.1, we typically just use minus 1, and then we interpret it as responses per second instead of the amount of time needed to response. And so in this case, I have to add in 1,000 into the numerator because the original data are milliseconds and not seconds. Easy. And then we get this nice model, everything works out, we're happy. And that's actually it from me. As I said, it's a nice little package and has good extensions. I'm happy to take any questions. It's all linked on pre-talks, by the way, so if you go there, you can actually see all this, and if I went too fast, you can look there, and it's also done as a nice article thing. Thank you.
Thank you. What are your questions? So, can you remind me how I do? I mean, what kind of data would I want to fit with this transformation?
Well, it'd be very typical that like you're fitting a linear regression model of some type, whether mixed or classical, and your data aren't, like the residuals are not normal, and you don't want to like kind of just pick a transformation out of the hat. And so this kind of suggests like maybe you should take the log of the data, maybe you should take the reciprocal, maybe you should look at the square of the data, and this will help you figure that out. So that's the idea behind it. It's actually a very old technique, like the from 1964, and it's not really taught anymore, unfortunately. But I think it's pretty cool.
Okay, great. Thank you.
Thank you.
There's one question.
So you can fit the box-Cox transformation on on a model, right?
Yep.
And if the model has several covariates, what does it try for each covariate?
Oh, so what it does is it does the different transformations, so the different possibilities, and then it's a nonlinear optimization problem. So it does a transformation, and then it refits the model on the transformed data. And so then you get new estimates for that. And then it does the next possible transformation and does this. It doesn't actually do like a grid search. It properly uses a nonlinear optimizer.
Isn't it a multi-dimensional search if you have several covariates, which you can box?
So you do the transformation and then you fit the model. So you do transformation, model fitting. In the model fitting process, it just uses mixedmodels.jl or GLM or whatever. And it's just that model fitting process. So the search space is the search of possible transformation values, the lambdas.
On each
and
covariate?
then you do the maximum likelihood fit on each of the lambdas.
So it's on each covariate?
It's searching over the space of possible lambda values. So if you look like here, this is the search space.
Just on the dependent variable?
Just on the transformation. So it's doing a transformation and then refitting the model each time.
Okay, so there's...
Yeah, you're transforming the response.
The response, yeah, but you can also transform the inputs.
This does not, the box-Cox transformation does not touch the inputs.
Okay.
This is purely on the response.
Thanks.
Thank you. Then let's thank the speaker again. Okay, next up we have Jamie from the University of Nottingham. Welcome.
Thank you. Can you hear me? Okay, great. So today I want to do a talk walking you through how I created Majoko.jl. So this isn't specific to the package Majoko, and I just thought this would be useful for anyone who might want to wrap a C library and access it from Julia. So this is some work I did with a colleague, Nick Barbara, at the University of Sydney. So a very small amount on what Majoko actually is and why we actually want to access it from Julia. So this is a really short video. It's not my video. This is from a group at DeepMind. And they're able to sort of train these simulated agents to play football. And this is a really cool application. And it's reliant on the actual physics simulation underlying it and the visualization techniques inside as well, which is what the Majoko engine does. And we thought we want to do things like this, so we want to access Majoko from Julia. So our other option would be to use like the Python API, and I'm sure everyone doesn't need me to explain why we didn't want to do that. So what I want to talk about today is sort of how you can replicate this process, maybe for a package that you're interested in and that's sort of specific to your field. So first of all, we'll go over what a JLL actually is and how you make them. You might have heard this term a lot, so hopefully you'll know what that is by the end of the talk. And then we'll talk about, once you have this JLL, how do you actually use it? How do you call the functions that you've taken from the underlying C library? And then also, how do you make this actually easy to use on the Julia side of things? So to create a JLL, I would recommend you use Binary Builder. There's nothing special about a JLL package. All it has in it is a sort of specification of all of the artifacts, which are like the precompiled binaries or shared libraries that a user would need on their platform to be able to use the code there. And you can create this manually. Don't, it's not worth it. Instead, you can use a brilliant package called Binary Builder, which has had a few talks at this conference already, and it makes the process far more straightforward. So to actually use it, you just install the package like you would any other package, and they have a wizard as well, which is sort of an interactive workflow where you can specify which package or which source code you want to download, and you write you have an interactive bash script on a Linux platform that you can use to actually compile the code. And what it will do is it will generate a file called buildtables.jl, which is just a script that takes the steps that you did in the wizard and makes it into just a Julia script so it can be reproduced. And I'll go very quickly over what this script is. So you just define the name of your package and some versions. You tell it where to find the source code. You give it essentially a bash script that will compile your source code and create your shared library. You tell it that it will create a shared library, for example, and you can also specify executable binaries as well. And then finally, it just calls the buildtables function. So what you can do is you can run this script with some arguments from the command line and deploy it to a local package on your system. And I recommend deploying it locally first just to test things out and see if it works. But ultimately, what you want to do is create a PR into this repository. It's called, I think it's called Yggdrasil, but I don't know how to pronounce it. And this is just a big repository full of these build tarball scripts for all the JLLs in the Julia ecosystem. And when someone approves your PR, it will get merged into this repository, and they will run your script and build it for all the platforms, or build the JLL for every platform, and register it in the global registry. So really, you don't have to do much at this stage. So once you have your JLL, how do you actually use it? The JLL doesn't contain any actual Julia code that you can call. All it has is these artifacts for a specific platform, and some code that like loads them into memory when the user loads your package. So for that, we turn to clang.jl, which is a really good package for actually generating your binaries. And so what we want to do with this is create a package that the user would load in. So instead of loading your JLL, you load your package like Majoko. I recommend you use PKG templates to create the original source. There's documentation on the webpage, but you'll get a directory structure that looks kind of like this. And then what we want to do is create a folder where you can sort of put all your scripts and all of the code to generate the source code automatically. So I recommend creating a new environment for this. And you also need to specify this TOML file, which is just options for Clang. On their GitHub page, they have an entire file that tells you every option and what each option means. And we also need to just write a script in Julia just to actually run Clang. And this is what the script looks like. It's pretty small. All it's doing is loading the JLL that you've built before and Clang. And then what the JLL will contain is the path on your system to where all of these binary artifacts that you built with Binary Builder, where they are on your system when you add the package. And this will give you also the headers from the library. And together with the options that you specified for Clang, you can build the actual bindings. And so what do these look like? They essentially just look like very thin wrappers around a C call. So for Majoko, there are literally like there's about 300 functions. So I didn't want to write this for 300 functions and then manually specify what each of the types were. So Clang can save you a lot of time here. It also converts all of the C structs into Julia structs. To be honest, they're pretty one-to-one mapping. But again, it's not something that you want to do manually. And it also converts things like enums as well. So having that, you get a very C-like library that you can call from Julia. So with the few minutes that I have left, I'll just sort of explain a few things that we did to make this actually easier for users of Majoko to use. So the first thing is no one really wants to manage pointers, right? You're in Julia, it's a memory managed language. You don't want to have to free every pointer that you make from your library. So Julia has a way of, in the constructor, you can specify like a finalizer or a destructor and point it towards the C function that will free the memory correctly so you don't get any memory leaks. I would highly recommend people do this. Also, Majoko has a Python binding, so they can. So it had a bunch of documentation in there that we could just scrape directly from the source code, and we basically wrote a script to generate Julia source code for the documentation. And you can also override these methods: get property, set property. So instead of your users dealing with pointers, you can convert them into objects that they're used to, like arrays, for example. So this slide just tells you the roadmap of what we've discussed. And if you want to access the slides afterwards for reference, you can have a look at this QR code. Great. Thanks for listening. Anyone have any questions?
Thanks, Jamie. So we have time for 1 or 2 questions.
Can it handle C++ as well, or only C packages?
So if you do a C++ package, you'll use Binary Builder exactly the same. That would be fine. But to generate the bindings, I think there's a package called CXX wrap instead that will do it for the C++. Okay. And it actually looks quite easy to use from the documentation. So you just swap out the Clang step with the CXX step.
Okay, thank you.
I mean, you need a C ABI. So for you might, if the C++ package has a C API, then you can use that also.
Hi. Did you by any chance use anything from the previous Majoko JL package that was in Lyceum?
Yeah, so we used a lot of their visualization code, which basically it was like a thin wrapper around their. Majoko had a bunch of C functions that called OpenGL, and it was essentially calling a lot of that code. So yeah, we took the code for the visualizer over, but we remade the entire library from scratch, apart from the visualizer.
Okay, thanks, Jamie.
Great. Thank you, everyone.
The next speaker can already come in front. Is Attila here? Okay. Next up would be Joanna. Are you here? Not yet. Which one? Yeah. That's yeah. Great. Yeah. Ah, okay. Welcome. You know about the cards? I will show you a yellow card when there's 3 minutes left, and a red one if there's 1 minute left. Oh, sorry. In a minute. Great. Next up, we have Attila. Welcome.
Thank you. My name is Attila Saraiva Quintela Soares. I'm a PhD student at the University of Alberta. Let me see if I can use a mouse here. Okay, so here at the University of Alberta. And my advisor is Mauricio Sacchi, as is in the presentation. And I'm here to present a package that I developed last year called Sequential ZFP Compression.gl, out of core multi-array compression. I'm part of this signal analysis imaging group, as you can see here in the corner. So this is the package. I changed the name, actually. So in the schedule is sequential compression. I changed the name to sequential ZFP compression because I don't plan to implement other compression algorithms. So it's just sequential ZFP compression.gl now. And here I use this ZFP compression.gl package as a dependency developed by Milan Kloer, and also tile iteration.gl developed by Tim Holly and other contributors. And the package is being registered. It's in the timer for 3 days for the auto merge, but is in the process. So I work with geophysics, and the problem that I have in geophysics is that I have a linear operator that is basically a wave simulation, but it's linearized, so you have like two wave fields actually. So you have the background wave field, this one, which is equal to this one here, and a perturb wave field. And in the forward simulation direction, I calculate both of these wave fields at the same time. So this is the first iteration, second, third, fourth. So it's okay. We don't have to do anything about it. You just calculate it and it's fine. But in the adjoint version, you actually go from the last time step to the beginning. But it's inefficient to recalculate this every iteration that you have in the backwards direction. So you go like this. If you had to recalculate the background wave field every time, it's very inefficient. So what we can do, you can just store it. So you can store it in a disk file, whatever. The problem is, if this array is super big and you have many iterations, then it becomes unfeasible. It doesn't fit in memory, neither in disk. Or it might fit in disk, but it might be very cumbersome. So what you can do is use compression. There are other techniques like checkpointing and stuff like that, and many people here might be already familiar with it. But the solution that I propose is just using lossy compression. So this is the problem. Imagine that you have an array of 1,000 by 1,000 by 1,000 with the precision. You have 8 gigabytes. If you have 8,000 iterations in your forward simulation, you use a finite difference. And 100 simulations, 100 shots in this case. It's just a nomenclature from geophysics. And then you have 8 terabytes, or 800 terabytes. And per shot, per simulation, you have 8 terabytes, which is a lot. So how can you reduce that load? So here comes the ZFP compression algorithm. The ZFP compression algorithm tries to create a floating point compression engine that is lossy, and you can control the amount of lossiness that you're comfortable with. And let's talk about it. So the first step is to divide your array into blocks of 4 by 4 in this case because it's 2 dimensions, but it can be 4 by 4 by 4 for 3, and so on. And for any blocks that are incomplete, you just pad with zeros, and it works. And you do a bunch of stuff, like can convert to signed integers and use a binary representation, bit shift plus truncation, linear orthogonal transform, reorder elements, bigger first, convert to nega binary. I'm not gonna get into details, but you can always read the paper from I don't know how to pronounce it, from 2019. What you get in the end is a binaries. So we are compressing float 16. So and here is the number, the values in the block. In this case, it's 4x4, so it's 16. And we also have 16 in this direction too, because we have 16 bytes or bits. After we done truncation, we might have less, but let's consider the case, the ideal case that we didn't reduce, we didn't do any truncation. So in this case, here is a bit plane. So this is organized in the rows. These are different numbers. And in these columns, you have bit planes. What does that mean? I did some reordering, and the negative binary representation makes it so that the first bit is always the most significant, which means that if you ignore all of this and you only use this, supposedly you have a lossy representation of your number. And if you use 2, so if you use 2 bit planes, then you have 2 bytes that you are associating with it, and so on and so forth. So imagine that these are the binaries that I already done a bunch of compression here. Now I want to figure out how many bit planes I want to use. So the stopping point for how many bit planes I can use can be parameterized by rate, for instance. In this case, the number of bit planes is limited by the number of bits that I want for each digit in the block, so it's normalized. Precision is the number of bits for the whole block, average. And tolerance is the max absolute error for the whole block, for the values. 3 minutes, all right? Right. Oh, shit. So let's be quick about it. So this is iterative process. So in the first compressor that I developed in memory, so I just compress it, put it to a vector. Here, I divide into the last dimension, I compress into different files. And the files are limited by the number of threads. Here is some code examples. So I have a compressor here, and I can append a few arrays and check if it's the same. In this case, I'm doing lossless compression, and then I can save to a file and then export load later. And I can define the type of compression that I want. If I use in the multi-file, I can define the path, or multiple paths, rate, precision, so on, and tolerance. I can check if the artifacts are conserved. They are. I can check how the space saving goes, and in fact, the space saving is pretty good. So it's a linear relationship for the rate. For the tolerance, it varies with the data. The speed is pretty good, but it varies with the number of threads that you have. So in this case, you have a minor, a lesser execution time per iteration for the final difference if you have a high number of threads, which makes sense. And you can see here that the time per iteration for the multi-file compressor is bounded by the just using saving to array and saving to a disk, which makes sense too. So final thoughts. Multi-file compressor offers excellent performance and much potential for further improvement. Probably can compose it with domain decomposition. And there is implementation of the FP algorithm in CUDA, and this might be a future work on it. And I wanted to acknowledge my advisor, my sponsors, Milan Chloe for the ZFP compression.gr for merging my PR, the audience, and thank you. If you want to take a look at the repository, please do. And thank you for your time.
Thank you for your talk. Questions? So
Thank you.
You used that in simulations, right?
Yeah. In this case, wave propagation simulations.
Yeah. How much in practice can you compress things before the simulations become untrustable?
I only compress the background wave field in this case. So the simulation itself is done uncompressed. I only do for the enduring part. So this part here. I only compress this one here. So it only affects the correlation between this uncompressed field and this compressed field. So is not too big of a deal. I made a presentation on another convention, but it was for geophysics, that I showed that the difference is not too big, and you can actually get away with compressing this field. Of course, if you do a very lossy compression, then it becomes bad. But
Okay, thank you. Okay, next up we have Ashutosh.
Hi, so I'll be speaking about hidden PD. Okay, so solving PDs using numerical methods do not scale that well in higher dimensions because the curse of dimensionality. What curse of dimensionality is basically that computational cost and memory cost increases exponentially as we, try to solve PDs in higher dimensions. Now, hidingpd.jl is a Julia package that implements various deep learning based algorithms to solve a specific set of PDs. What these specific set are, I'll get to it in the next slide. But yeah, in higher dimensions using deep learning, we'll see how that scales. There are some existing methods like MLP and deep splitting that also deal with partial integral differential equations. There's already a talk about it. I suggest you watch it. So what's new? So I'll be demonstrating three algorithms, NN stopping, NN Kolmogorov, and NN param Kolmogorov. And then I show a unified API of how to interact with hidingpd.jl. Okay, so these are the two kinds of PDs that hidingpd solvers aim to solve. The difference between the two is the first term. As you can see in PIDs, the first term is integrated over X, and in the parabolic PD problem, the first term is just a nonlinear function. Yeah. And this is the algorithm support and API. All solvers in hidingpd solve parabolic PD problems, but only deep splitting and MLP are for PIDE problem. The API is pretty much the same. There are some keyword arguments that you have to provide when you are using a specific solver. For the solvers that I am demonstrating, I'll show them. Yeah. Okay. So for the next three solvers, it's again a very specific case where the nonlinear. So the next three solvers, NN stopping, NN Kolmogorov, and NN param Kolmogorov, the nonlinear term is going to be 0. So this is what the basic form of PDs would look like. Okay, so NN stopping, this is for optimal stopping problems. You can it applies to PDs of this form. They're usually called as obstacle PDs. You usually find these problems when you try to exercise American or Bermudan style options where you have an option to exercise early. And here high number of underlying assets give rise to high dimensional optimal stopping problems which are difficult to solve due to curse of dimensionality that we discussed. So the goal here is to find the optimal stopping time and the optimal payoff, which is given right here. Yeah. Okay, so this is what the API looks like. You define your constants, then you define your drift, volatility, and then you define the models, the optimizer, and the algorithm, and then you hit solve like you would do for any other SciML problem. So here are some results. The first plot is analytical payoff versus the predicted payoff by the model. And as you can see, we scale up to 500 dimensions for this case. The training is done on CPU for now because it does some scalar indexing, but we're working on getting a GPU version of it. I'm sure it would be great. Yeah. So the next one is NN Kolmogorov. Here we deal with Kolmogorov PDEs of the form, yep, where by the way, it's for both forward and backward Kolmogorov equations. This one is a forward one where we have an initial condition and we aim to solve for the terminal condition. And this solution is distributed all over X, so you get a distribution at the end of it. Okay. And this is the API. I'm skipping over the API parts to save some time. Yep. The first plot is when we solve the heat equation in 2 dimensions. This is the error landscape. As you can see on the edges, it's pretty bad. So yeah. And the training time, NN Kolmogorov, by the way, is supported, has the GPU support. So that's training time versus dimensions as we scale. Okay. Now the most interesting, and in Param Kolmogorov, we try to solve families or parametric families of Kolmogorov PDEs here. So now we get a solution over all parameters, time, and X. Some example of Kolmogorov PDEs include heat equation, like we saw in the previous slide, and Black-Scholes PDE. Now we're going to look at some downstream cases after this. So this is an example of a basket put option. So there are a few nuances here. So because we find the solution over all parameters, now we have to provide a parameter domain as well. So we find a solution over all of the domain of the parameters, like here. And yeah, so you define your net, and yeah, the rest is the same. Yeah, so one of the downstream use case of NN Param Kolmogorov is because you find a solution over all domain of a parameter, you can easily do parameter estimation on real world data. So for demonstration purposes here, I had simulated using Monte Carlo simulations, and this is for 3 dimensions. And I do a basic for loop to fit some parameter estimation loss. Okay. And then we can also do sensitivity analysis with NN Param Kolmogorov. So the problem that I was discussing was basket put option. So usually in finance, the Greeks are of interest. These are delta, vega, or theta. So we are specifically talking about vega here, which is your price by, which is how your price varies with sigma. And yeah, here are some results. The first one is a GIF to show how we fit on the parameter estimation with the data, and the second one is predicted vega versus Monte Carlo vega. Yeah. Questions? Wait. So there is some future work. Like I said, we need GPU support for NN stopping. We can also support MTK. And sensitivity analysis is not very robust at the moment. You need to train with some nuances. So we are going to make it robust. So yeah, that's all.
Thank you.
Thank you.
We're happy to take your questions. In the back.
Thank you for the talk. It's not directly my field of expertise, so if the question is not so. I understand that high dimensional PDs is like really high dimension, but what about like dimension 6 or 12?
Oh,
like
it can scale to
plasma?
that. Yeah, if it is of that form, it does work. So in our tests, usually the dimensions are 6 or 10. So yeah.
Ah, okay. So, you know, do you know the applications like in plasma physics where one has like master equations or Fokker-Planck equations?
Fokker-Planck, I don't know, but I know about the Fokker-Planck equation. I have tried NN Kolmogorov on that previously, and it works. Yeah.
Ah, okay, great. Thanks.
I guess it's a forward Kolmogorov equation, right? If it's
I think so, but
okay.
I mean it comes from an SDE, but that's all I know.
Okay.
Okay, let's thank the speaker again.
Thank you.
The next speaker can come up here. Okay, so next speaker is Joanna, and without further ado, let's start.
All right, thank you all. So my name's Joanna. I'm a PhD student at MIT and affiliated with a group called Seismics, where we contribute to developing an end-to-end Julia workflow for molecular simulation. And today I'll be talking about a package that I'm developing called Karen, which is a library of algorithms for enhanced molecular dynamics for active learning. So earlier this week, Rachel Kirchen and Michael Herbst gave an excellent keynote, which motivates why we care about multi-scale modeling and computational material science, where numerical simulation models can help accelerate the process of materials characterization and discovery. Even with advancements in high-performance computing, simulations at the quantum scale using DFT remains cost prohibitive for systems larger than a few hundred atoms. And for that reason, we're interested in developing machine learning anatomic potentials, which serve as surrogate models at the atomistic scale, which are trained on quantum calculations and achieve the same accuracy at a fraction of the cost. Now, the challenge here is the same as with any machine learning model, which is that the model is only as good as the data that you train on. So we operate in the regime of small data sets, meaning that our models can be subject to high uncertainty. And in molecular applications, the landscape of configurations that we train to is often highly multimodal and high dimensional. So we can understand this using an illustrative example. Consider that we have a carbon monoxide molecule, which has a double well energy landscape. Each well corresponds to an equilibrium state of the molecule with a different bond length. We sample configurations along this landscape by a process called molecular dynamics, or MD simulation, where we simulate Newton's equations of motion for the atoms. Now, carbon monoxide has a strong bond, meaning that it takes a large amount of energy to pull the atoms apart and change its bond structure, which corresponds to a tall barrier between the energy wells. And since the force acting on the atoms is related to the gradient of this potential energy landscape, then we see that the trajectory remains confined to this local minima, and we never observe the molecule in its second equilibrium state. This is a major problem when we use MD trajectories to generate training data for machine learning models, because models trained on an insufficient subset of the state space can lead to unreliable predictions. So for this reason, we're concerned with this question of how do we drive MD simulations to explore new regions of the state space? So this is one component of the larger objective of active learning for scientific machine learning models. The goal here is that rather than take the naive approach of simulating a bunch of data for your training set, which can be very expensive and inefficient to label, we want to be more intelligent with our selection and query new data, which maximally improves the accuracy of our model. So our team at Seismics has a Julia package for each step of the active learning loop. The first step is to generate data by sampling. This can be done using enhanced samplers in the package Karen, which is built as an extension to Molly, developed by Joe Greener. This package interfaces with anatomic potentials for defining the form of our machine learning model with trainable parameters. The second step is to generate trajectories and then select an optimal subset of that data to then label and append to our training set. So Karen also includes methods for data subset selection methods, and labeling can be done using reference calculations, such as with DFTK, developed by Michael Herbst. The third step is to train the model on the augmented data set. So potential learning is our package containing functions defining objectives for learning the parameters of the machine learning model from data. And finally, the fourth step is to evaluate the accuracy, stability, and performance of our updated model for characterizing various material properties. So atomistic QIs is our package now for calculating these quantities of interest using the updated model. And the idea here is to apply these steps in an iterative loop, which is terminated after we've reached some threshold of model accuracy. Here the colored package names are in-house packages developed by Seismics, which importantly interface with tools that are developed by our collaborators at Julia MOSIM. And today's talk focuses on Karen, which is the master package that ties together the others as dependencies. So this package is structured to maximize composability and our active learning loop with each time step. We have a simulate function defining the equation of motion used to advance the trajectory and sample our next configuration. We evaluate whether a trigger has been activated for stopping the simulation and updating the model. If it is activated, then we define a scheme for selecting a subset of the data to label and append to the training set. And finally, we retrain the potential on the augmented set using an objective defined in the learn function. So the idea here is that users can flexibly exchange methods that are specified under each of these abstract types. Among simulators, we can run standard samplers for MD simulation or enhanced samplers, which encourage diversity and exploration. Among triggers, we can have a fixed trigger over a fixed number of time steps, or adaptive triggers based on some criteria related to uncertainty, extrapolation, or diversity metrics. Among subset selectors, we can make a basic selection, such as a random subset of the trajectory, or we can make an adaptive selection using an algorithm such as d-optimality, DPPs, or CUR. And then finally, among learning problems, we generally train using least squares loss and energies, forces, or both. One could also frame this into a Bayesian inference problem through the definition of a likelihood and prior over the parameters. Okay, so I'll show a few examples of how Karen can be used to implement various active learning algorithms in literature. So for example, one could implement FLARE by choosing velocity relay as the simulator. Model updating is triggered when the trajectory reaches a region of high uncertainty as measured by a Gaussian process. We choose a subset of data with the largest uncertainty estimates for retraining the model using a standard objective function. Uncertainty-driven dynamics, or UDD, can be implemented as a custom simulator where we introduce an additional biasing force that drives the trajectory toward regions of high uncertainty as measured by the variance of predictions from an ensemble of models. So these could be the same neural network model with different initialization of the weights. And then similarly, we choose data associated with high uncertainty for appending to the training set and updating our model. Finally, Karen is home to a novel active learning algorithm that we're currently developing called Stein Variational Molecular Dynamics, or SVMD. And it works by introducing repulsive biasing forces that drive the trajectory away from the existing training set to encourage diversity in the resulting dynamics. So here's a quick demo of the method, where to the left we see contours of a 2D machine learning potential trained on an initial set of data in red, and the trajectory is shown in green. Here, the initial training data is concentrated in one well of the potential, and the goal is to see how efficiently our simulator can sample from the other well.
Sorry to interrupt you here, but we're out of time.
Okay, yeah, so I'll just run through the rest of this to show you that with our custom simulator, we're able to more efficiently sample from the state space and have the contours of our machine learning potential recover the true contours. And here are a few kind of summarizing points. With this, I'll wrap up my talk, and thanks for your attention.
Okay, thanks, Johanna. In the interest of time, I would say we go right on to the next talk. So come forward. Okay.
Okay.
Okay, and the last talk before eventually the break comes and then the last keynote is Emmanuel.
Thank you, everyone. My name is Emmanuel Lima, and I'm going to talk to you guys about CAD-CAD-JL, modeling library for generalized dynamical systems. So first of all, just a bit about me. I am a senior research software engineer at Block Science, an R&D firm from the United States. And I'm also the lead engineer for the CAD-CAD project. That is the software I'm about to show you guys. So here's my email and my GitHub accounts if you guys want to reach after the presentation. So first things first, what is CAD-CAD-JL? So CAD-CAD-JL is a library to orchestrate and simulate trajectories of generalized dynamical systems. It stands for Complex Adaptive Dynamics Computer-Aided Design. It's just a mouthful, but you guys are going to get a clearer picture of what the library does in a moment. Basically, it's an open source framework for generalized dynamical systems. It's a generalization of the idea, of the theory of a dynamical system. We already have a legacy version of the library that has been developed in Python that implements a subset of that theory of GDS, meaning that it does simulations based on a subset of that mathematical framework. We are working right now on a reference implementation in Python that actually implements the whole of GDS, all possible simulations that could be done in GDS. And we are also, hence why I'm here, working on a performance implementation in Julia that also implements the whole of GDS as well. So what is a dynamical system? So very basically, dynamical system is a representation of an observed phenomena that includes a state, which is basically the snapshot of a system, and includes rules about the time evolution of that system. And it comes in many flavors. So the evolution of a dynamical system, for example, can be entirely deterministic, or it can be subject to non-deterministic influences, to randomness, that is external or internal of the system. Typical, quote-unquote, dynamical system evolves a state x over time t according to a certain function, and that function can vary over time. So either the attributes of that state or the function that actually evolves the system can vary over time, can be random. So the state transition of that system would be a function of the previous steps, of the previous state. So that's how the time evolution of a system would occur. And it can be continuous or discrete. So that's the very brief overview of the regular dynamical systems as we learn in universities. But in CAD-CAD, we simulate generalized dynamical systems. And the difference is that a GDS does not have to just talk about numbers, just talk about very contrived examples that are numeric in nature. A GDS can have a state represented by a generic data structure. So for example, in this picture, the data structure we're talking about have a lot of different types, and this is where a language with a good type system such as Julia comes in. For example, this particle here has types, strings, floats. It could be integers, it could be user-defined types, and it could also be nested. So, for example, this particle data structure has another data structure as one of its types inside of its own data structure, that is, for example, the Cartesian plane. So that's basically the main difference between GDS and a regular dynamical system on the context of computer simulations we're talking about here. A brief rundown of GDS from a mathematical standpoint. So basically a GDS is a pair, H and X, where the H from X to X, as we talked about on the regular dynamical systems slides, is a state transition map, and X is a state on a state space. So X is the big X, capital X, is actually the state space. So this is just to say formally that GDS is a bunch of states that belong to the space of all possible states, future and past, and a function x that is basically the composition of all of the functions that time evolutes the system. And a GDS is that pair that is the function and the space. And when the function is applied over and over to elements of that space, we have a trajectory. So the trajectory is basically the list, or the vector, for example, of all the states that were produced during a simulation. Right? But more specifically about CAD/CAD's model of computation. So we saw here that a generalized dynamical system, we must have a space and states inside of that space and a function that evolutes the states. Those functions on CAD/CAD's model of computations, we call them blocks. So those blocks are basically small units of logic that accept specifically some kind of input and output a specific kind of output. So here on this picture, you can see, for example, if you focus just on this process 1 here. On this process 1, you can see that it has a yellow D and a green B on the box. This means that, it's just to clarify that process 1 is a block or is a function that only accepts data of type D and only outputs data of type B, right? So by doing that, I can ensure that I can make very complex logic, very complex kinds of state transformation by concatenating, like Legos, different pieces of blocks, different logics that can transformate my system. This is going to become a bit clearer when I get to the actual example. But for example here, process 1 accepts data of type D and outputs data of type B. So after process 1, the data that comes out of process 1 is a data of type B, so it has to be put inside another block that accepts type B. If I try to put it on a block that accepts another kind of type, so the library would raise an error. So the pipeline of all the blocks concatenated in a coherent fashion is what we were calling here on this formalized notion the H, right? So this whole pipeline would be run for each time step of the simulation. We can have, for example, on this process 2 here, blocks that are endogenous. So for example, they don't accept any data. They don't have any data coming in, but they output a data, in this case, of type E that is red, for example. So it would output this data, and another block would have to accept it, in this case, the block process 3. And the logic itself inside of those blocks is just regular Julia code. So what is important from CAD/CAD's point of view is that the data that is flowing from one point to the other of the pipeline is always type safe. It's always the correct kind of types that is coming in and coming out. If you take a look at process 5, when process 5 finishes digesting its data, finishes its logic, it outputs type D, yellow D, and that is fed back into the beginning of the pipeline again to process 1. So because we have this closed loop here, then we actually have a simulation. Because the next state that is produced, the next step on the simulation is always based on the previous step. So that's how we have a time evolution of a generalized dynamical system. And the importance of using block diagrams becomes clear when we look at this picture here. So there are these 3 properties that a block diagram gives us when doing simulations in CAD/CAD. So first, it's tiering. I can take a look at this picture here, and I can zoom in and tear it apart and examine the individual logics of each of those processes. So I can look at just process 1, process 2, 3, 4, or 5, and take a look what kind of data is coming in, coming out, and the logic it's producing. I can tear it all apart and look at it individually, but I could also pick up another pipeline, another set of blocks, and just concatenate it if the kind of data that is outputted from the other pipeline is the same as it is inputted on this pipeline. So I can tear a pipeline of blocks into smaller blocks, I can analyze the individual blocks, and I can link them back together. So I can zoom in and zoom out as I want during the modeling of a system. So basically, so why did we in the first place started CAD/CAD/JL? So it was our experience that when doing model-based systems engineering, the systems engineers, they were using expensive proprietary software for modeling like MATLAB. And CAD/CAD is basically an open source alternative to MATLAB in a model-based systems engineering context that plugs very easily into other SciML frameworks and libraries, but also on the greater Julia data science environment. So you can start a simulation in CAD/CAD, and then you can use it to train a model, or you can use the resulting trajectory and plot it using the usual Julia libraries, because in the end, the trajectory is a regular Julia data structure, right? Internally, it's basically just compact structs in memory. And the main selling point is the schema. Basically, the schema is the shape of all the types on this data structure, the data structure that represents my world, the world that I am simulating. That is completely arbitrary. I can put any kind of types that I want. They can be high performance types, they can be types that I defined, they can be strings. If, for example, my world is just strings that I evolve over time according to certain rules, my schema, my space can be just strings. So it doesn't matter. CAD/CAD is agnostic to all of that. So the use cases for CAD/CAD that we envision is basically to engineer and validate complex systems, so to do design digital twins, to do model-based data-driven decision-making, and also live health monitoring and forecasts, as in operational digital twins. So these are basically the biggest use cases we are envisioning for CAD/CAD for the future. So I'm going to just present a very simple example of a prey-predator simulation on CAD/CAD on how it would be written as a model in CAD/CAD. This model right now, it can't be run completely from top to bottom because CAD/CAD is a work in progress. The library is in an alpha state and is still being heavily developed. But basically, this is the API as it is designed today. So this picture just demonstrates how the simulation is going to behave, so the actions of the simulation. So we have those first four light gray, I guess, boxes: the predator births, prey births, predator deaths, and prey deaths. And then each of those boxes are blocks. So each of those boxes are like the ones I drew here, are small and atomic units of logic that digest data from a certain type and spits data on another type. So we have those functions here, those blocks here, and then we have the blocks join naturals, natural causes, and hunt. Basically, the light gray, light green boxes say that how the populations of predators and prey will change on an environment based on natural causes, let's say, like a lightning or an accident, a disease, or whatever. And births, just births. Join naturals, as you will see in a moment, is a block that doesn't have a logic by itself. It just concatenates all the data that comes out of the green boxes into one data structure. So this is just to demonstrate that a block can have a logic that doesn't actually digest the data that comes in, but just reshapes it. And natural causes is basically just actually updating the population of prey and predators based on the natural causes of the green boxes. And the hunt block here at the end is actually how the prey population is going to decrease based on predators eating them, basically. And the simulation loop is from natural causes to hunt, and then back to natural causes to hunt, and then you see the time evolution of the predator and prey population. So basically, the first thing that a modeler would do, he would declare all the spaces that capture the simulations I'm trying to do. So we can do this with a macro. That population, we have to declare that it's basically an identifier together with a type. On the syntax of cat-cat.jl, it must have a type because, as we said, like those types are basically the contract that must be obeyed about the data that is coming in and coming out of a block. So I'm going to say that the prey population is an unsigned integer because I don't want like a negative population. Predator population is also an unsigned integer. And I asked like the Julia runtime to choose the size for me based on where it's running. So no size annotation. Also, I created another space called delta population. And that delta population is an integer, so it can be negative. So that delta is basically just the amount of change of a population during the simulation. And the joined delta space is a data structure that is going to be concatenated on this join naturals block. It's going to be a bit clearer later on. Here, I'm just setting the parameters of the simulation. Those parameters are just regular Julia named tuples. I'm just putting like a rate of births for prey, a rate of birth for predators, a rate of death for both of them as well, some constants, and this sim params here is just the configuration of how I want to run this simulation. So I want the number of steps to be 1,000, so I want the simulation to run that pipeline, the whole pipeline, I mean this whole pipeline, to run 1,000 times. I want the parameters of that simulation to be these that I declared just before, and I want it to run one time, because what I can do is to actually create a list of trajectories. So that would be a matrix. So I can run that simulation a number of times, change the params slightly, and to see how slight change on the parameters can change the graph of the evolution of the predators and the preys. So the blocks in cat.jl are just regular Julia functions, but they have this specific signature. So they have to have a domain, and that domain must be a space. They must have a codomain, and that codomain must also be a space. And optionally, can have parameters. So these parameters that I pass here are is the named tuple that I defined here. The logic that goes inside of those functions can be any. It's up to the modeler. But what I'm doing here is basically just randomly choosing how many predators are going to be born, preys as well, and how many predators and preys are going to die of natural causes. The domain is the shape or the size, the space of the data that comes in, and the codomain of the data that comes out. Here, I'm just joining all of the delta population spaces that came from these blocks here. So if you see the codomain of this block, or the data that comes out, is a delta population. And a delta population is just one integer. So I want to join them all together by this block here on a codomain that is a joint delta. If you go here, the joint delta is just a bunch of delta populations, 4 delta populations, right? So I join these 4 functions here, 4 blocks here, on just one data structure. And that is exactly what this yellow block here is doing. So by joining them, I can just say that this block is digesting, is actually bringing together a lot of delta populations. You can see that the domain of this block is multiple, and its codomain is just one. It's this joined delta. And finally, I have the two blocks that actually do the simulation. Is first the natural causes. So it accepts population as a domain and a joint delta also as a domain. And as a codomain, it returns population. So it accepts a population, the delta of that population, or how that population is going to change, and then gives back the population updated. That population is updated by the natural causes of that environment. And then the hunt block will accept the population as the domain and give back a population as a codomain, meaning it will pick up the population that comes already updated from natural causes, is going to do a hunt, and then give back a population updated with the results of that hunt. If you see the logic, I picked up something that's very simple, just for an example's sake. So it basically says for every hunt, there is a 5% decrease on the size of a prey. But I mean, the logic is agnostic and be any kind of Julia logic, because at the end, a block is just a regular Julia function with this signature. And then I define the initial state. So I'm going to say that initially, the state of my population is 1,000 preys and 15 predators. I write this pipeline. So the pipeline is basically a DSL that we are devising to say basically how this figure is becoming this string. And I then ask for the CAD engine to run, and this run produces this trajectory. And that's basically it. So CAD is, I don't have more time, but CAD is work in progress. We would like if you guys could join us. And thank you.
Thank you for the talk. Any questions?
Thank you for the presentation. I have a simple question. I noticed that despite being a dynamical system, it seems like it's not limited to dynamical systems that can be expressed in an analytical formula, like a math formula, right? It can be anything really, right?
Yes.
But would I be able to just write a custom function that does, I don't know, like solves the wave equation or something like that, and add that as I forgot the name that you use to define these blocks. Can I just write any function and compose a simulation using that?
Yes. It's completely agnostic to what you can do. So you can write a block that does anything on any kind of shape, any kind of space. So it's completely up to you. Yeah.
Thank you.
Thanks. So your framework that you presented, I consider it agent-based modeling with the additional restriction that you also have to declare a pipeline. That's how I understood at least the concept of the generalized dynamical system. And at least the simulation you presented, I know I could be doing with an agent-based modeling library. So now my question is, what are the scenarios or in which situations would I prefer using this framework of an agent-based modeling library?
Because I think that this very simple example, yes, it could be done on agent-based modeling library, but there are others that wouldn't be so great, at least in my opinion. Like, for example, I could, on those pipelines here, I believe make pipelines that are like very complex that the current agent-based modeling libraries wouldn't be able to do, as far as I know, or it would be very complex to do. And also, when I'm doing the modeling, CAD allows me to do a lot of stuff on those data structures, on the spaces, to create further spaces that I haven't seen another SciML library doing. I could be wrong, of course, but I could, for example, do Cartesian products and start from a data structure and create lots of other data structures afterwards. And I can, like I put here, I can zoom in, zoom out on the pipelines, and I can create very different pipelines by focusing on small pipelines and then making the pipelines reusable. So in the end, you make a pipeline that is basically a library, and we are doing a final pipeline. Your final pipeline is going to be just the input or the include of several other pipelines. And those pipelines can be parts of them running parallel and so on.
Thanks. In Julia, the agent-based modeling library, agents.jl, is not part of SciML. And perhaps you could check it out and compare there more concretely, because at least so far I could not imagine something that I couldn't do with this library. I can totally appreciate that I could do this easier with this library, but it would be good to know what are the pros and cons so that the users can know better or be better informed which one they can choose for which type of application. But thanks a lot, though.
Actually, I have a question. Do you know how? First of all, do you know the workflow management languages like KNIME and stuff, which also have kind of these blocks that you can move around and then shuffle data through?
Yeah, I think I have seen them. Yeah.
How does it compare?
Those languages, I don't think that they do the exact same thing that CatCat does, that is picking up the data structure with data and operating on them and creating trajectories of various other data structures. I mean, the trajectory itself, that's basically what CatCat does. I don't know that they do that, so I think.
Okay. And do you have the interface, like the user interface, is it nowadays text-based, or do you have like a GUI?
So it's text-based nowadays, but the idea is to be able to create like that kind of picture, like to compile down diagrams into the pipeline string automatically. So, but right now the user would have to write the string according to a specific DSL.
Okay. Other questions? If not, then this was your last talk before the final events. So have a nice JuliaCon and see you tomorrow at the hackathon. And let's thank our speaker again.